यांची पोरगी आहे बाबा द्यायची काय म्हणते तो काय करायचं आता काही पर्याय नाही पण मेन जे आहे ती व्यक्ती मला पाहिजे हे नाही करायचं मला माणूस पाहिजे ज्याला हे करायचं तो बघेल ना
Dr. Meshram.
Yes, sir. Good morning, sir. Yes, sir. Good morning, sir.
Good morning.
Yes.
Yeah, confirm whether all the resource persons have joined or not.
Yes, our resource person Nirish Reva Prasad sir has joined, and Professor Rajneesh Kamath will join at 1 o'clock, and Aniruddha Pandit sir will join within few minutes. So,
yeah. Honorable Nirish Reva Prasad sir.
He has joined, sir. Yeah. He has joined.
Okay.
He's with us, sir. Yeah. We will start on time, sir.
Yeah, okay. So still 2 minutes left.
Yeah, sir. 2 minutes are there.
Okay.
Yes, Aniruddha Pandit sir has joined, sir. He has joined.
Yeah.
Okay. So.
Yeah, we can start now.
Yes, sir. I'll start. Yes.
Go ahead.
Yes, sir. Very good afternoon to everyone, and good morning to our resource person who have joined us from South Africa and UK. I am Dr. Leena Mishram, Assistant Professor in Zoology. I'll be your host for the day. On behalf of Mahatma Phule AC College, I take this opportunity to welcome you all for the International E-Conference on Advances in Material Science, Bioscience, and Information Technology, jointly organized by Faculty of Science in association with IQAC. It's a great pleasure for me to welcome our resource persons for the day. It's an absolute privilege to welcome today's keynote speaker, Professor Nirish Reva Prasad sir, Senior Professor, Department of Chemistry, University of Zululand, South Africa. I welcome today's resource person, Professor Rajneesh Kamath, Senior Professor, Dean, Faculty of Science and Technology, Shivaji University, Kolhapur. I welcome Mr. Aniruddha Prasad, Project Manager, Project Management Pharmaceutical Product Development from Scotland, UK. I welcome Honorable Principal Dr. Ganesh Thakur Sir, Chairman, Organizing Committee, and Principal, Mahatma Phule AC College, Panvel. I must welcome Vice Principal Dr. Rajaram Patil Sir. He is the Head of Geography Department, Vice Principal Dr. N.R. Madhvi, Head of Economics Department. I also welcome Vice Principal Mr. A.G. Rokde Sir, Convener of the conference and Head of Zoology Department, Dr. Pramod Thakur, Co-Convener, Dr. Girish Gund, Organizing Secretary, and Mr. Sopan Gove Sir, IQAC Coordinator. They have worked hard to ensure that this conference becomes successful. A warm welcome to all the dignitaries, eminent guests, HODs, professors, faculty members, research scholars, students of different streams who have joined us from different parts of the world. We are honored to have you all with us for the e-conference on advances in material science, bioscience, and information technology. This conference is an opportunity to share knowledge and experience in science and technology. It is also a deliberate effort to provide an opportunity to the budding scientists and research scholars from various disciplines to interact and present their research work in front of the international scholars and stimulate research practice in their respective discipline. The theme of the conference is the ultimate need of an hour, as science and technology have expanded their wings, making our life easier and more comfortable. We have with us Honorable Principal Ganesh Thakur Sir, ex-secretary of Rayat Shikshan Sanstha, a prominent academician, an excellent administrator, and a dynamic personality. Under his dynamic and visionary leadership, he has brought several laurels to the college. To name some, Best College Award by University of Mumbai, A grade by NAG, and the status of college with potential for excellence status from UGC. Sir is also honored with numerous prestigious awards. To name few, Panvel Gaurav Puraskar, Raigad Bhushan Puraskar, Best Principal Award by University of Mumbai. Sir, your action always inspires us. Sir, you encourage us to do the best. Over to you, sir.
Thank you, madam. At the outset, I pay my tribute to great social reformer and visionary educationist of Maharashtra, Mahatma Jyotiba Phule and Karmavir Bhaurao Patil for their selfless service to the masses. Dignitaries present online for this international e-conference, keynote speaker, Honorable Professor Nirish Revaprasadu, Chairperson of the South African Research Chairs Initiative, Department of Chemistry, University of Zululand, South Africa. Resource person, Professor Rajneesh Kamath, Dean, Faculty of Science and Technology, Shivaji University, Kolhapur, India. Mr. Aniruddha Pandit, Project Manager, Pharmaceutical Product Development, Belsil, United Kingdom. All the participants across the world, principals and directors of different institutes, vice principals of our college, coordinator of Internal Quality Assurance Cell, Mr. Sopan Gove, organizing secretary, Dr. Girish Gund, convener, Mr. Anil Rokde, co-convener, Dr. Pramod Thakur, members of advisory and organizing committee, head department of chemistry, physics, zoology, botany, information technology, mathematics, and biotechnology. All the participants from different states of India, faculty members, research scholars, and dear students. I am extremely delighted to welcome you all on behalf of Mahatma Phule Arts, Science and Commerce College, Panvel, for this international e-conference jointly organized by Faculty of Science in association with IQAC on the topic Advances in Material Science, Bioscience and Information Technology. Our college is affiliated to University of Mumbai and is run by Rayat Shikshan Sanstha, which is one of the largest educational institutes in Asia. Our parent institution basically works for overall development of those strata of the society to uplift their educational standard. Our founder, Bhaurao Paigunda Patil, was honored with Padma Bhushan Award from central government and Doctor of Latest Degree from Pune University for his outstanding contribution in the field of education. Our college was established in 1970 with a vision to provide quality education to all classes of the society. And in true sense, we are marching ahead with the same principles to achieve the excellence in the field of higher education. Our quest for excellence is reflected through some of our outstanding achievements in the recent past. A grade in third cycle of NAC accreditation with CGPA score of 3.18. Best College Award from University of Mumbai. And DBT Star College Grant from Department of Biotechnology, Government of India. It reminds me a famous quotation of our ex-president, Dr. APJ Abdul Kalam. The difficulties in the life do not come to destroy you, but to help you realize your hidden potential and power. We work on the same line to utilize COVID-19 pandemic for the organization of academic activities. We successfully organized 15 international and national webinars in the previous academic year. Today's international e-conference is the 9th online conference of this academic year. Dear friends, material science is the branch devoted to the discovery and development of new materials. It's an outgrowth of both physics and chemistry, using the periodic table as its grocery store and the laws of physics as its cookbook. The Material Genome Initiative in June 2011 at Carnegie Mellon University ex-president of United States of America, Honorable Barack Obama, announced the Materials Genome Initiative, a nationwide effort to use open source methods and artificial intelligence to double the pace of innovation in material science. He felt this acceleration was critical to the US global competitiveness and held the key to solving significant challenges in clean energy, national security, and human welfare. And it worked. By using artificial intelligence to map the hundreds of billions of different possible combinations of elements like hydrogen, boron, lithium, and carbon, the initiative created an enormous database that allows scientists to play a kind of improved jazz with the periodic table. This new map of physical world lets scientists combine elements faster than ever before and is helping them create all sorts of novel elements. These tools have helped to create the meta materials used in carbon fiber composites for lighter weight vehicles, advanced alloys for more durable jet engines, and biomaterials to replace human joints. We are also seeing breakthroughs in energy storage and quantum computing. In robotics, new materials are helping us create the artificial muscles needed for humanoid soft robots. The lithium ion battery, which today's power everything from our smartphones to our autonomous cars, was first proposed in 1970s. It could make it to the market until the 1990s and didn't begin to reach maturity until the past few years. But producing enough of them to meet demand has been an ongoing problem. Tesla has stepped up to the challenge. One of the company's gigafactories in Nevada churns out 20 gigawatts of energy storage per year, marking the first time we have seen lithium-ion batteries produced at such large scales. Lithium-ion batteries will continue to play a major role in renewable energy storage, helping bring down solar and wind energy prices to compete with those of coal and gasoline. Graphene is a single layer of carbon atoms tightly bound in hexagonal honeycomb lattice. It is nearly weightless, but 200 times stronger than steel, conducting electricity and dissipating heat faster than any other known substance. This super material has transformative applications. The conversion efficiency of average solar panel is a measure of how much captured sunlight can be turned into electricity and lingers around 16% at a cost of roughly $3 per watt. Phosphites, a light-sensitive crystal, and one of our new materials, has the potential to get that up to 66%, which would double what silicon panels can muster. Nanomaterials make lighter automobiles, airplanes, baseball bats, helmets, bicycles, luggage, power tools. The list goes on. Researchers at Harvard built a nanoscale 3D printer capable of producing miniature batteries less than 1 millimeter wide. In medicine, drug delivery nanoboards are proving especially useful in fighting cancer. The applications are endless. The term over the next decade, the impact of the very, very large, small is about to get very, very large. Technology is unavoidable in our everyday life because life without technology is meaningless in today's dynamic world. Technology which brings together tools to promote development, use, and information exchange has its main objective of making tasks easier and the solving of many problems of mankind. The first and the foremost purpose that technology serves is communication. Social media and other technological applications have brought families together, Today, we can find long lost schoolmates over Facebook, Twitter, Instagram, and we can reinstate our communication. In fact, we can even communicate with world leaders, prominent figures over these platforms. Communication is required in professional fields as well, and technology ensures that we can communicate with the world from where we are. We cannot imagine our lives without a smartphone, but there was a time when there was no mobile phones at all. Globalization wouldn't have been possible without internet. The fact that we can connect and work from any part of the world is because we have internet. We can have client needs and requirements from all over the globe, and we can assimilate information and process delivery because we have internet. COVID-19 pandemic has proven that internet can keep our lives going even when we are locked down in houses. The branch of life science is constantly being shaped by new technological breakthroughs and advancement in knowledge. The search for COVID-19 vaccine has caused the life sciences community to reinvent the way it develops vaccines. For the first time, biopharmaceutical companies and government agencies forged strategic partnerships to accelerate the process of vaccine research and development. Although monoclonal antibodies were first identified by the research scientists years ago, they have recently been modified to create antibody drug conjugates with the ability to identify cancer cells and deliver targeted radiations more efficiently to these areas. Another important ingredient in the field of biotechnology is the so-called biosimilars. Like monoclonal antibodies, scientists have been aware of biosimilars for some time. By using different compositions that vary only slightly from existing drug brands, biosimilars can deliver the same result as current immunotherapy and targeted therapy drugs at a lower cost. Customized medicine is one of the hottest trends in biotechnology. Cell and gene therapies, along with customized drugs, are used to treat the precise variant of an illness. They are created by manipulating human cells and genomes. The emerging trends are important because they remind people about the critical role that biotechnology plays in developing new medicines, guiding healthcare best practices, and supporting the health and well-being of people all over the world. I am confident that the keynote speaker of the webinar and this international e-conference and the resource person will enlighten us with their scholarly talks on the theme of this conference. I am really grateful to all the participants for their awesome response by sending 85 research papers to this e-conference organized by our college. Before I conclude, once again, I welcome you all for this international e-conference. Thank you very much.
Thank you, sir. Thank you for such a warm welcome and the brief introduction of the theme of the webinar. Now I request Professor Anil Pandey, sir, from Department of Chemistry to introduce our keynote speaker. Dr. Anil Pandey, sir, has completed his postdoctoral research from United States. He is also a recipient of the most prestigious award, Tata Scholar Award, and 2 of his patent has been granted by IPR India. I request Anil Pandey, sir, to introduce our keynote speaker, Honorable Professor Nirish Revaprasadu, sir. Over to you, sir.
Thank you, Dr. Leena Mishra. Am I audible, Dr. Girish?
Yes, sir, you are audible.
Thank you. It's my great pleasure to introduce Professor Nirish Revaprasadu. Professor Nirish Revaprasadu is the Professor of Inorganic Chemistry and South African Research Chair Initiative Chair in Nanotechnology at the University of Zululand. He obtained his BSc honors from the University of Natal, South Africa in 1994 and PhD from Imperial College London, UK in 2000. He has published 250 research articles and 30 book chapters. He has given more than 80 lectures at national and international conferences. The research focus of the chair is on developing routes of the delivery of high quality materials. The initial work was on second 6 semiconductor materials such as cadmium sulfide, cadmium telluride, lead sulfide, lead telluride, and lead selenides. The current focus is on earth abundant materials using metal complexes as a single source precursors. The material of interest are bismuth, Fe, nickel, cobalt, antimony chalcogenides. AACVD, that is aerosol assisted chemical vapor deposition, and hot injection route are used to prepare the binary and ternary materials. Work on metal chalcogenide binary, ternary, two-dimensional, and carbon nitride metal chalcogenides composite system for application in energy generation and storage is also an area of interest. In particular, the materials are studied for their efficiency in the hydrogen evolution reaction, oxygen evolution reaction, and supercapacitance. Now, I invite Professor Nirish Revaprasadu for his keynote address. Over to Professor Nirish Revaprasadu.
Can you hear me? Can you hear me?
Yes, sir, you are audible.
Yeah, okay. Great. Can you see the screen?
Yes, sir, it is
Okay.
visible.
Thank you. Okay, it is a great pleasure to be part of this meeting, and I must thank the organizers, in particular Professor Anita Pandey for the invitation. And it is an honor to be part of the meeting and to share the work that we are doing in my research group at the University of Zululand. So the title of my talk is Functional Nanomaterials from Precursors, a step-by-step approach to synthesis, characterization, and energy applications. Now, I will give you an overview of the big field, and then I will focus for students mainly some of the practical steps involved in making precursors and doing chemistry, which will then take you to solving bigger problems in the world. Okay. Now, I like to start off with this slide because it makes you think about something, and many of us, including Professor Anil, who's working in the field, can identify with this. Now, there are two types of research proposals when you want to do research. One is that you can do exploratory research. In other words, you start with an area and then you keep exploring without really thinking much about what you're doing in your next step. And that was a type of research that we did for a long period of time, where we started with precursors and we just moved on from one to another. We started with one metal, you did another metal, and so forth. One ligand, the next ligand. So that was very exploratory without really having a idea why we were doing the next metal. Now, then the world has changed, and we are now taught, or we are now told, to do research based on hypothesis. Now, what does this mean? So it means that you have to solve a problem. You don't just do research, or you don't just do explorations, you have to know why you're doing it. So you have to tackle a problem and present a solution to the problem. And when you do that, you then work towards solving the problem. And you can make a hypothesis as to how you're going to solve it. And at the end, you will either accept the hypothesis or reject it. Now, many students might find this difficult or tricky to understand, and even researchers, because we're not trained in many ways to look at hypothesis-based research. Social sciences do it all the time, but the hard sciences, are still getting used to this idea. So in any research proposal that you present your hypothesis and you find a problem. So just as an opening topic. Now, if you're looking at problems, one of the biggest problems in the world is energy. So there's always a search for clean and renewable energy, which will replace fossil fuels. And there's a huge interest in energy storage and conversion systems. Okay, so this is an international problem. So there's the problem, and we need to solve it. And one of the ways to solve it is using by splitting water to give you hydrogen and oxygen, giving you what is known as green hydrogen. And you can store this hydrogen in batteries or in fuel cells and so forth. So coming to green hydrogen, this is an interest of mine in the last few years because some of the materials that we work with are good catalysts, electrocatalysts, to convert water to hydrogen. So just as an introductory slide, which shows you the importance of hydrogen. It's on the part of 30 countries that are releasing roadmaps. We've just released ours with many projects and funding in the pipeline, including in China, Europe, United States, now have proper plans for introducing green hydrogen into the energy mix. And the reason why we say it's green is that it is, the whole process is sustainable or carbon neutral. We need an electron, an energy source, and it can come via solar, wind, hydro, ocean, or the geothermal method. And you need an electrolyzer, which will convert the water to hydrogen. Okay, so this is just a very, very simple scheme. So what you see on your left is purely sustainable, and there's your electrolyzer, which is then the material science part of it. So we need catalysts that will use this energy and produce hydrogen. Now the catalyst, there's only one material that's known, or the gold star material, which is platinum. However, platinum is very, very expensive and very, very scarce. So people and scientists are now looking for alternative materials or catalysts in place of platinum, or composites that will use less platinum. Okay, so that's where we come in. So there's another nice pictorial of what happens in the whole system. So you have the clean energy generated through hydro or wind or solar. You add water, which is tap water or desalinized water, and you produce your hydrogen, and you can store it as a gas or a paste, or convert it to ammonia or hydrocarbons. So this is the general scheme of how the whole thing will work. And this is purely green, not blue or gray hydrogen. This is okay. So what happens in the whole process? So that's the big picture. So we need materials that can overcome this band gap of 1.23 electron volts for the forward bias reaction. So photoelectrochemical materials are specialized in convert the water molecules into hydrogen. So these are the catalysts. And how do we choose them? It has to have these properties. And the work involves identifying and developing durable and efficient materials and systems. And there's the cell. This is what happens in the cell. Water splitting happens at the photoanode, which makes up. So you have two reactions. One is the generation of hydrogen at the HER, and the other one is the oxygen at the OER reaction. So these are the electrochemistry that is involved. I'm still learning a lot about this because I'm not an electrochemist. I'm a material scientist, but yeah, so it's a simple system. That's what our collaborators tell us, that these are the reactions that we need to look at, and these are the two reactions that we monitor and we evaluate. So we evaluate the HER and the stability and the output. Okay. What happens to the hydrogen? You can convert it to water in a fuel cell, and then you have another reaction there, which is the HOR. So that's basically the science behind the whole system, and the reason why people are very excited about the field. We are interested in the electrocatalysts now. So just as an introductory slide to nanomaterials, and I'll come back now later and give you examples that what we've made. So we are looking at materials in the 1 to 100 nanometer range, and we normally we are very obsessive about size, that they should be small. However, in our new applications, we find that size is not that important. We look at shape, and I'll show you nice images of particles that are in different shapes. We can look at composition, which in other words, the collection of particles that will give you a material. And more importantly, on the left is the variation in composition. So we can design materials with different composition, in other words, binary, ternary, doped materials, bimetallics, and this is now a highly how can I say, specialized field where you don't actually have to do the reactions. That's why we come back to the hypothesis. You can actually do a lot of modeling and find material that you may think will be important, have important properties for application. So there's a whole lot of what they call machine learning and AI work being done on finding new materials, and there are specialized companies that actually do this sort of work. However, we are chemists. We still do work in the lab, so we do it via trial and error. Now, so the underpinning science behind the nanomaterials is obviously well known. So we know that we have these monomers or seeds that will join together to form nanoparticles. So you have the atoms or the monomers, which then form particles, and the particle itself can orientate, and you can by oriented attachment to form assemblies and then final solids. And all of this happens with the notion that you have an organic ligand on the surface, which helps to keep the particles apart. And then when you need them to be assembled, it depends on the ligand itself, how the assembly happens. Example, always good to give you for students a good photo or image of a nanoparticle. This is some of my work, just cadmium selenide surrounded by tetraphosphine oxide. So you have a single particle with the ligand. You cannot see the ligands because of the density of the diffraction. So all you see is the lattice fringes under the microscope. Excuse me. Lead sulfide is always a nice material to see on the microscope, and you can see the cubic lead sulfide, and then a single cube. You can have a rod-shaped lead sulfide, and these are modulated by excuse me, by the surface ligand. Again, more anisotropic material. This is bismuth sulfide, antimony sulfide, antimony selenide. Some of our recent work where we were not really worried about the shape, but these are the natural shapes that occur when you try and make this material. So what are quantum dots? So quantum dots are some nanomaterials that are very, very small, and they undergo what is known as a quantum confinement effect. And they mainly in materials which show good luminescence and absorption. Excuse me. And this is an example of cadmium selenide, where you have different colors purely based on the size of the material. And so this is a very common photo. And the explanation for this is the increase in the band gap formed when you have an electron hole pair from the particle, and if the electron hole pair is equal or smaller than the size of the particle, you have what is known as a quantum confinement effect, and you have an increase in the band gap. And this is shown or applied in quantum dot LEDs, TVs. This property is now sort of used as an application to make LED TVs with using quantum dots for excuse me, showing you very, very good picture quality. Now, so that's just some of the applications of nanomaterials and some of the issues surrounding what we're trying to do. Now, how do we make these materials? We've used one of the routes is the single source precursor route, where you make a material and then you thermalize it in a high boiling point solvent. Excuse me. Or you can spin coat the material, or you can then just thermalize it without a solvent, what we know as the melt method, which we use quite often now. Or you can deposit it in a CVD kit, aerosol assisted CVD. So you put in a suitable solvent and you heat it, and it forms a layer on films. I'll show you some examples of all these techniques. Now, why do we use single source precursors? Because the metal chalcogenide or metal oxide, metal nitride, or whatever you're trying to make is already in the molecule. It's generally low temperature decomposition. In other words, we're not using temperatures above 500. It's generally between 200 to 300 degrees. The complexes are generally stable, and they are quite suitable for nanoparticles with thin films. We can use dual source, and that's the old work where it started with dual source, but you end up using metal alkyls and highly toxic starting materials like phosphines or hydrogen sulfide, and generally higher temperatures. And you have also problems of moisture and pre-reactions. So this is a well-known route and reported route. There's a lot of literature on this work. Work done a lot in India as well by the Jain group, and Dr. Shivram Gaj at University of Mumbai does work on this field, and indeed Dr. Palve as well. Now, what is the requirement of a precursor? It has to be pure, so the chemistry has to be very, very perfect. So you need to make ultra pure starting materials. If your starting material is not pure, then you're not going to get a pure material. So in our group, we really stress on making precursors that are extremely pure. It has to be a known synthetic protocol because you have to have repeatable routes. So you can't make something which you cannot repeat. Obviously, toxicity is an issue. The precursors must not be toxic. So we stay away. We've now moved away from lead and cadmium and mercury. We are looking at mainly earth-abundant or non-toxic metals. It should be stable and scalable. So you need to make a lot of the precursors. You can't just make 1 gram or 2 gram or half a gram. You need to make 5, 10, or 20 grams so that you'll have enough for applications. And obviously, cost is always an issue. You should know that your starting material shouldn't be too costly or too scarce that the price is too high. So we stay away from exotic starting materials. Now, this is the part of the talk where students will be more interested in, and it's more student orientated. Now, if you want to make a precursor, how do you go about it? You obviously need a method, and the method can either be published or maybe you're trying a new method. You need chemicals class where you need to do a risk assessment. You need to know whether your reaction is going to be dangerous, whether it is going to be a risk to your colleagues or to the environment. So you need to carry out that risk assessment, and that's mainly in your material, your starting materials, the chemicals which are labeled. So you need to read the bottle with the labels on it, whether it's toxic, whether it needs to be done in a fume hood, whether so what are your risks? And then obviously you start the experimental work. You need to purify your product, characterize it, and then you can use it for your application, either in nanoparticles or nanomaterials or thin films. And obviously, once you've made them, you need to characterize the material. So you characterize your precursor, and then you characterize your material. Yeah, so the method, either it's a known compound, so it's easy. You can work out the equation, maybe more than one method. You can choose the method. If it's unknown, then you start with the family. It always comes from a class, a family. Whether it's dicarbamates or xanthates or phosphonates or whatever. And then you start with a similar method, and you can improve, modify, or change it. So that's quite simple. So some rules. These are again very, very elementary things, but it's always good to revise them. So in our lab, you never work alone. You always have a lab partner because you're doing chemistry, and chemistry can be dangerous. You need to know where your first aid kit is, your fire extinguisher, eye bath. Okay, so always use safety glasses that you should know, lab coat, gloves, or masks for toxic or corrosive metals. Never use dirty glassware. You always clean your glassware in either base or bath. You should always use glassware that you have. You don't need to buy or go to stores to get. And the most important thing is you need to know your chemistry in terms of your first year chemistry, where you need to know stoichiometry. So one of the things that you'll do is to weigh your starting materials, and you need to know which balance to use. So always use the correct balance. So 2 decimal for if you're using a gram scale, 3 or 4 decimal for sub-gram scale. So I spoke briefly about stoichiometry. You need to know that in chemistry you work not in grams or in weight, you work in moles. So you need to know your ratios. So it shows that if you look at this equation, 1 portion of amine, 1 portion of carbon, and 1 portion of sodium hydroxide, and then you use 2 portions of sodium bicarbonate. So 1:2 or 2:1 or whatever. So you know how to convert mole. This is first year school chemistry, right? So number of moles is grams of molecular weight, and you convert everything to moles, and then you react. Many students make mistakes with this formula. So always a common mistake is not to add the hydrate and water crystallization. So make sure you include that when you do your molecular weight. So wrong quantities of reactants, okay, 1:2 or 2:1 will give you incorrect results. So adding A to B is like tipping 1 buck, okay. So discard the full trade and keeping it. So many students also make mistakes about about filtrates and product or precipitates, it's important to know which is which and which is important. Not understanding the reaction and starting blindly mixing chemical. Does it need dry conditions? Why is it moisture or oxygen sensitive? So yes, so please, when students do the reaction, you need to be aware of these issues. Okay, not planning ahead, so you use glassware or equipment to quite. Okay, so piece of is missing, so you need to have all your glassware in one spot. Don't start something and then you realize you need ice, and then there's no ice, and then you have to go to ice machine. So make sure you read your protocol well before you start your work. Okay, using shortcut, tipping interval and drop by. Yeah, many students try and rush reactions. Many of our reactions require slow addition, which is drop-wise addition. So you don't just tip it. Some chemicals are hygroscopic. Proper care is required to open bottle. Okay, so you need to know again your what you're working with, and not understanding the difference between heating, refluxing, and so on. Okay, so the last point is quite simple. You need to always work in neat and tidy, and should be labeled and organized. Don't use the gloves when they are not required to be used. Yeah, many people use gloves for no reason. Also, don't use the wrong size of glassware. If you're doing a reaction for 1 or 2 grams, use a 250 ml flask, not 500. Getting too small quantity or not enough, so proper character. You need to start with enough to give you enough so that you can characterize it. Many students are guilty of this, where you start your reaction and then you leave your work and you go away and you ask your friends to look after the reaction. So make sure you're always at your desk doing your work, and you need to monitor the reaction and record observations. Okay, so not understand the difference between heating and that I've spoken about. Using wet solvents for moisture sensitive, so you need to dry your solvent. So you distill your solvent, you store it under nitrogen, and then you need to also always calculate the yield of the product. Okay, and these should be kept in a lab. So there's some of the what you would need if you using liquid nitrogen, where you trapping or you doing the reaction. So you have to be careful with liquid nitrogen and make sure it's always available if you need it. Or dry ice acetone mixture is just as good. Okay. So heating, we normally don't, in our work, we don't use Bunsen burners anymore, mainly hot plates or heating mantles, silicon oil, oven, and now we're using furnaces. And so this is example of a photo of a tube furnace, which we do the ACVD reaction and the melt method. This is set up for a reflux. Many people forget about the water in and out. So your reaction is in the flask with your cooling on the top. Now, once you get your product as a chemist and as a synthetic chemist working with complexes, you need to crystallize it. So you can obtain the crystal structure if it's unknown. Then you can do solvent extraction, sublimation, distillation, chromatography, etc. So crystallization is a technique we use to purify compounds. So you can mainly insoluble or mostly organic filtration, some unreacted materials. So there are 3 types. So you always have impurities, and these could be unreacted or products resulting from reactions within the complex. It's a process which removes all types of impurities. So you need a very, very pure product, and it involves how do you crystallize. So this is an art in itself. So you select a suitable solvent, high dissolving power at high temperature and a low dissolving at low temperature. High or negligible dissolving power for the impurities so that they can either be filtered or remain, and a solvent with low boiling point for easy drying of the So no single solvent is proved to be useful. Then you can use a mixed solvent. So it's mainly trial and error. You try various solvents for dissolving your material, and then you then crystallize them. So the solvents must be immiscible at all temperatures, and the solute must be insoluble in one of the solvents. Okay, the solute must be soluble in another solvent. So these are if you are using the mixed solvent. So you crystallize the crude product and you dry it. Okay, yeah. So these are some of the tricks of crystallization. You can use activated charcoal, which has a polishing effect. You can heat the solution you're boiling, then you filter off to remove the insoluble, including the charcoal, and you leave it at room temperature in the fridge to produce the crystals. Okay, then you collect the crystals by filtration. So you collect your crystals in the filter paper, and then once it's in the filter paper, you need to dry it. So you can dry it on the top of an oven or in a desiccator or vacuum flask where you can vac on it. So you apply the vacuum and you can trap the solvent in liquid nitrogen on the Shen gland. Okay. So once you have your product, you can then determine the melting point, either microanalysis, CHN analysis we normally do, infrared, NMR, mass spec, X-ray, or thermal TGA. So these are the basic techniques that you will use to identify your starting material, which is your precursor. So most of you have seen a melting point apparatus. So you need to take at least 3 readings. You need to observe carefully and any change in color or slow melting. So you don't wait for it your material to decompose. You can just wait for him to sublime on heating. Okay. Microelemental analysis. So you need to know what you have in your product. So the percentage of elements in what ratios. Okay. Infrared. You run an infrared to determine the functional groups that you should know that are present in. So it confirms what you have. Okay. So there's a typical spectrum of infrared. Then you can do UV analysis, so you can determine the band gap, these are for materials. You can determine band gap, size distribution, fine structure. If you have your metal complex, you can determine the alpha max and so these are the typical UV data that you can get from your analysis. The bottom ones are for your So these are for your nanomaterials. This is cadmium selenide and cadmium selenide UV and photoluminescence. Okay, I'm just going to skip through this. So NMR, most of you are aware. So you can determine the chemical shifts, coupling constant, nuclear spin of your material. This is a typical NMR spectrum. So mass spec, you can determine molecular ion peak, base peak, fragmentation pattern. It's always good to do a mass spec. Okay. And then finally, X-ray crystallography. If you have a nice crystal, you can then determine the single crystal, the quality of it, the R factor, disorder, bond length, and so forth. So this gives you a unique fingerprint of your material. And these are some examples of crystal structure. And the crystallographer will do this for you, and he has programs that will help you to determine the structure of your material. Now, so this is our business. We've done a lot of crystal structures and published a lot of work with the unique or novel structures. So we always attempt to make something novel, and these are very early work on the cadmium and zinc zirconides. So that's just basically for students to understand what goes on in making the precursors. So We do a lot of that in our lab. Once you've made them, then what do? You destroy them, right? So you create and you destroy. So you made all your complex. Now you put it in a high boiling point solvent, and you're going to get your nanomaterial. And you can vary concentration, temperature, capping group, reaction time, just to get materials properties that you want. Okay. And there's a setup for the reaction. It's on the Schlenk line. So you need a flask, round bottom flask, and a heating mantle under reflux, and then you have two neck flasks. So you can inject your precursor in one and septum, and you can monitor the reaction with the thermometer on the other side. Okay. So once you've done that and you've injected it, and you can then characterize them. And one of the techniques is the electron microscope, the transmission. Yes. Yes. I can hear you.
Yes, sir. You are audible.
Okay.
Yeah.
Yeah. Okay. Yeah. So these are antimony sulfide nanopegs, we call them, or nanocubes, or nanohexagons, nanosheets, nanorods, nanowires, nanodots, nanospheres. So you can get a whole variety of shapes.
Excuse me, sir.
Okay?
Your slide is not changing. So
okay.
please check, verify it.
Okay, why not? Does it change now?
Not yet. No.
Oh, hang on.
Can you make it a presentation?
Okay, man.
Slideshow.
Why is it paused? You tell me my okay. Okay. I think you'll get it now.
Yeah.
Yeah. Sorry. Thank you. Yeah. So
Not
you can
yet.
get.
Yeah. Okay. Go ahead.
Yeah. Nanopegs, nanocubes, nanohexagons, nanosheets, wires. Okay. And these are purely obtained by varying the reaction conditions. So gives you some sort of control over what you want to achieve. Okay, and we've done a lot of work, and there's a lot of literature on this, and a lot of it is trial and error. But we've now come to sort of, this is what I spoke about at the beginning, exploratory research, where you do many reactions, and we've done many to get what we want to achieve. Okay, and typically students make 20, 30 samples, and we do spend weeks doing electron microscopy work at a high cost. Okay, but purely because we want to explore and want to vary conditions to see how we can obtain different shapes and so forth. Did we ever use the materials in applications? Not at the beginning. Okay, so these were work papers and publications that didn't include applications, and we didn't really understand how the shape will influence the performance of the material, the functionality of the material. And so it was good work and a good time to publish work like this, where journals would accept them purely because of how the materials looked. However, the world and the field has changed so much in that people really don't care about the shape and size and how it looks anymore. It's mainly about the functionality, and that's where hypothesis-based research is required. You need to know what are you trying to achieve in doing the reaction. Okay, not just doing it and observing what you've done. So okay, just moving on, because this is quite nice work and interesting work on copper sulfide, where you got different shapes and chains and very beautiful images, which was published again in good journals. Yeah, we were using mixed solvent system, so you can use top and DT, and you can get a chain of particles and so forth. And we wrote about these, how this happens and what is the reason for this. Okay. Again, this is oleilamine in another solvent, I think it's dodecanthiol. Okay. These are different shapes again. These are tetrahedrons of copper sulfide. Again, nice photos and so forth. So there was a lot of work on copper and lead, and I showed you. Then many years ago, we wrote a review article in Chemistry Materials where we were looking at, this is with the late Paul O'Brien, on alternative materials for energy applications. And we were mainly interested in earth abundant materials. So we went into, so we left lead, cadmium, copper, and so on, and went into iron, tin, cobalt, and nickel. So nickel, by chance, we stumbled onto nickel. Nickel was well published, but we thought we could make a contribution. So, and then we changed the route. We didn't do the hot injection route. We were more interested in the getting a large amount of material, because the hot injection route, your yields are quite small. And one alternative or an alternative method would be to use a solventless route. So you didn't use a solvent. You took your starting material and you just heated it at a reasonable temperature. And the temperature that and the material that we chose, that the class of material was the xanthates. So the xanthates were not did not decompose at high temperatures, at very, very moderate temperatures. Okay. And so that's why we didn't use the diethyl carbamates, which we used for most of our career. So we use the xanthate-based complexes because of it's a lower temperature, and it's a known mechanism, which is the Chugev elimination, right? So it's quite easy to make xanthate, as easy as making diethyl carbamates, and so this is well documented. It's made very, very easily in the lab. However, you have to make it in large amounts, and it has to be pure. And then, so we didn't use the starting material to make nickel sulfide. Okay. So now this is where again the hypothesis-based method approach we used. Remember, I showed you nice, beautiful photos, and we did a lot of reactions. Now we just chose about 5 reactions. So even a whole chapter in a thesis done only with 5 reactions. Okay, so it was unheard of in our group, because students were doing 20, 30 reactions, and we said no, you have to form a hypothesis and then see whether it is true or not. Okay, so this hypothesis, or what we were trying to prove here, was the long chain, or the chain of the alkyl group, whether it affected the performance of the nickel sulfide and the phase. So we used ethyl xanthate and octyl. So ethyl, short chain, and octyl long chain. So same complex, but 2 different organic chain lengths. Okay, we made the 2 complex, so it's complex 1 and 2. And what we did was we were trying 2 different temperature, a range of temperature between 200 to 400. So how many reactions? Not many, right? So this is the data. So you can see that there is a temperature dependency. In other words, as we go from 200 to 400, the phase changes. You get an alpha nickel sulfide and beta nickel. So at 200, you're getting alpha, and at 400, you're getting beta. Okay, so that's one of our outcomes, right, from our hypothesis. Does temperature affect phase? Yes. Okay, so our hypothesis was temperature affects the phase. We tested it. Yes, it does. Okay, and then we've got the data to prove it. This is for complex 1. We did the same set of reactions. So if you look here, we did 1, 2, 3, 4 reactions, and here we did 3 reactions, okay, at 3 temperatures. So 250, 300, 400, and this is for complex 2, which is the long chain. And this is nickel sulfide, giving you the exact. So here we find that there is no change, okay. So for complex 2, the temperature didn't influence the phase, okay. So we then did the normal characterization, and then here you see the TEMs are not very nice or not beautiful as the ones that I've shown you, because we're not using a capping group. There is no external organic capping group, right? So you find that the materials are clumped and are quite, you know, stacked up, or you know, not very well dispersed. They coalesce, okay. There again, and this is nickel sulfide. So again, not very good looking, but we were not interested in the looks, okay. So these were from complex 2 at 3 temperatures, right? So next set of reactions. Now, so the next part of our study was, how does that phase influence the performance? So what did we find? So here you see NISO and NIS1, sorry, NISE1, SE2, SE3 are the short chain, okay, and NISO at the temperature is the long chain. So we did measurements on 4. And remember, NISA1 is alpha nickel, Ni2, temperature 2 is a mixture of alpha and beta, and then NISA3 is beta. So there are 3 different phases, or 2 phases and 1 mixed phase. And then the final one is the long chain. Okay. So what did we find? For the storage, this specific capacitance, we found that they had good performance, okay, 1287 and 1085. So for the alpha and beta, so both were reasonably high. We did the water splitting reaction for them, and we found here that the best results were for the NISE3, which was the beta phase NISE, okay, and NISO was 380 millivolts required for 10 milliamps per centimeter squared, whereas NISE3 only required 139. So OHEI we observed to be much higher for the Muller-Wright phase compared to the hexagonal. Okay, both samples were quite good. Okay, so that paper was published a few years ago in a good journal. Just done on 7 reactions, and we did the application for water splitting, just to see the effect of temperature on the performance and the Akka chain. Okay. The melt method is, as I've explained, it's quite well publicized now, and there we came up with the paper in about 2018, where we did a lot of ternary materials. So here you see silver bismuth sulfide, copper indium sulfide, copper gallium, copper iron, copper antimony, silver indium. So you can make a lot of ternaries, and these were all minerals that we were looking at, natural minerals. And this paper only had, many will know that in order to get a good publication, you need many techniques. But in this paper, we only did 2 techniques, the X-ray diffraction and the elemental analysis. So you don't need many if you have a good story. So there again, elemental analysis is very important for the ternaries. You need to know what is there. So you need an electron microscope that can do elemental TEM, right? So this is silver bismuth sulfide, copper indium sulfide, silver indium sulfide. These are the chalcopyrite type materials, right? Well publicized, but made by the new method. This is silver indium sulfide melt. Again, you will see that a lot of coalescence and not well dispersed, but We were not looking for that. We were looking for more crystalline materials, and that's shown here in the HR10. This is again silver indium sulfide via the melt, and silver bismuth sulfide. So this paper came out a few years later as well, where we showed you could get good quality and very pure, phase pure bismuth, silver bismuth sulfide. And these are some of the elemental TEM. And then again, we did measure the supercapacitance properties. Another interest is the Thai spinels. Again, these are nickel cobalt sulfide, copper cobalt, or copper cobalt chromium sulfide. And we've done a lot of work on this. So there's some nice papers. And in this particular case, I think I have it here. So for the nickel cobalt system, nickel cobalt sulfide, we were looking, again, our hypothesis here was to see whether the ratio of nickel to cobalt, how did it affect the performance? Do you need a pure ratio or impure ratio? In other words, purely stoichiometric or not so stoichiometric? And what we found, that I'll show you now, is that nickel-rich the ternary nickel cobalt sulfide, the nickel-rich phase, gave you better electrocatalytical performance, right? So wherever you added extra nickel, so it didn't have to be 1:1, it has to be excess nickel to cobalt, giving you better performance. Okay. So we called it, we labeled it off stoichiometry. So it was off stoichiometry, not exact stoichiometry. Okay. So again, very good electrocatalytic performance and OER and HER as well. We moved away in the last few years, or a year or two ago, away from the sulfur, or not way, but we were now going into nickel phosphites. So nickel phosphites also have different compositions. You have NiP, NiP2, Ni2P. So you have a whole box of tricks that you could perform on a nickel phosphide and see which phase gives you better performance. Okay. And how do you make nickel phosphides? You can make precursors as starting materials, which is the dithiophosphonates, right? Which are well reported. Okay, it's in the literature. We can do analysis of the TGA analysis, and here we find very interesting. And here we use the not the solventless route. We used the hot injection route. And when we use topo as a surfactants and we disperse it in top, remember the complex already has the phosphide, but we're still putting top, which is also a source of the phosphide. So we have Ni2P. When we didn't use the phosphide, we used octadecylamine, we formed the nickel sulfide. Okay. So the phosphide is not coming from the precursor, it's coming from the top. When we use HDA on top, we got Ni5P4 and so forth. And then you see, again, whenever we use top, we're getting the phosphide. So top is the, not culprit, but it's the main source of the phosphide, okay? Although our starting material had the phosphide. Okay. So that was quite interesting. So when we've done X-ray diffraction, then you can see different purity. It's important to get phase pure materials. Don't try and publish materials that are not phase pure. This is the morphology, again, not very good, but we were more interested in the performance. Okay. So we did supercapacity capacitance applications, and they were quite good. The Ni2P gave you very high supercapacitance, the 1672, which is quite good, and just as good as the ones reported in the literature. Okay. We did the HER reactions and found that it only required 235 and 256 millivolts to reach 15 milliamps per centimeter squared. Okay. So we did a whole lot of material, and I've not spoken about all in this talk. And there you can see a wide range. If you check on Google Scholar, you can Google my name, or on the databases, you can see that we've worked in quite a vast area of material, array of material. Okay. So I like to stop there and acknowledge the people that have done the work. I have 3 postdocs, and these are the current students. This always changes with time, and also the funding that I get from the government, from the university, and from some international programs as well. And I'm willing to take any questions.
Yes, sir. Thank you, sir. We have questions from the participants, sir. What are the limitations of single source precursor if they are unstable or hygroscopic? That's a question from the participants, sir.
So I don't understand. Is that, are you asking, is hygroscopic or unstable limitation?
Yes, sir. If the precursors are hygroscopic or unstable, are there any limitations for that single source precursor?
Yes, sure. Obviously, if you have to take, if it's hygroscopic, you have to take special precaution in handling them. I'm not sure how. Okay. So our aim is not to make hygroscopic precursors or unstable precursors. So yeah.
Okay. So we have one more question, sir. What would be the next generation material in the field of energy storage? That also is a question from the participant.
We're not sure. I mean, there was a question in the last talk I gave, and somebody mentioned lanthanides and actinides and in the periodic table. So maybe people are looking towards those. That's where it might be. Or I think there's still a lot of work to be done on the nickel and cobalt system. Nickel and cobalt seems the 2 best type of metals that gives you good performance. Yeah.
Okay, that's only two questions we had, sir. Thank you so much, sir. We are really grateful for the time and efforts you have given, and thank you so much for sharing your expertise on the functional nanomaterial for precursors, a step-by-step approach to synthesis, characterization, and application. Thank you so much, sir.
Thank you.
We now move to the next session. I request Mrs. Nandini Gaikwad to introduce our next resource person, Honorable Professor Rajneesh Kamath, sir, Dean, Faculty of Science and Technology, University, Shivaji University, Kolhapur. Over to you, Nandini, madam.
Thank you so much, ma'am. Good afternoon, one and all. It is my great pleasure to introduce today's resource person of this in-conference, Professor Rajneesh Kamath, sir. He is a senior professor, Dean Faculty of Science and Technology, Shivaji University, Kolhapur. He has 25 years of teaching experience in higher education. He has nominated as a reviewer in UGC for learning outcome curriculum for the framework. Also worked as a UGC nominated expert for adjudicating autonomy to various institutes in the Andhra Pradesh and the Telangana. He has a great research initiatives. He has published around 12 books and 17 book chapters. Also, he has published 176 research papers in different journals, which are published by IEEE, Elsevier, and the Blackwell Publishing House. He has guided 19 PhD students in electronics and computer science. In last 5 years, he has received the grant of ₹24 crore and in different projects as a principal investigator. Also, he has received the Young Scientist Award under DST Fast Track Scheme and also received a Best Teacher Award from Shivaji University, Kolhapur. Thank you, sir, for being with us. We are very much eager to listen your scholarly talk. I request Honorable Professor Rajneesh Kamath, sir, to deliver a speech. Over to you, sir.
Thank you so much. Thank you so much. Am I audible?
Yes, sir, you are audible.
Sure. I'd like to share my screen.
Yes, sir. You can share the screen.
I hope the screen is visible.
Not yet. Your screen is going to share.
No, I already shared from my side. Is it not appearing in front of you?
Yes, sir, it is processing. The screen sharing is processing. Just wait.
I'll just try the other way. Or is it
Sir,
okay?
please. Not yet. It is not shared. So try to another way if possible. Yes, sir. Now it is visible.
Just
Make
one
us, yeah, slideshow and.
Just 1 minute. Yeah. I hope you can see the screen. Hello. Can you please confirm? Can you see the screen?
Yes, sir.
Okay. So I was just hearing the address by Honorable Professor in the previous session, and that was all about nanomaterials. However, the theme of this particular session is slightly different. It is based on the information technology, and information and communication technology is now better moving towards a new paradigm, and that is called as Internet of Things. So I'll be talking about the information and communication technology in general, and many applications, because as you have seen, the professor was mentioning that there are a lot of you can say problems as far as the applications are concerned. A lot of work is going on towards the material science, and even our group is also doing a lot of work towards neuromorphic computing. And in neuromorphic computing also, there are many materials that we process, and we want to emulate the human brain by using the materials. A lot of work is going on. However, we are more towards the application orientation of the materials. And from that point of view, we'll be just going through this particular presentation. So I'll be just explaining you about the new computing paradigm. And this new computing paradigm that all of us are going through is a variable computing paradigm. So we have our smartphones with us, and that is the best example of variable computing. So the computers which can be there in our pockets, the computers which are there in remote controls, computers which are there in our televisions. However, we are able to see those computers. So that is a new computing paradigm which is coming, called as variable. Another paradigm which is more often we encounter is the fog computing. So you must have heard about the word known as cloud computing. Cloud computing. But now this is all about fog computing. So I'll be explaining this new term and the new technology which is coming up. And this is very close towards the IoT and the number of machines which are getting connected all over the world. So this is a new connection paradigm. And then all this requires the synergy between hardware, software, firmware. So we are moving from computing in time to computing in space. And then what are the applications of all this approach, and how new innovative business models are coming through? Because as we have seen that today's business models like Facebook or Twitter, they don't require much investment. However, they run on the customer's base, and this kind of new things are coming up with the information technology. Actually, I'll just go through, while going through this page is intentionally left blank. The simple reason is that now you have to forget about what the earlier lecture was there all about. It was all about the science and now moving towards the technology. And I believe that technology leads to a lot of creativity. This is my old picture when I started working with Goa University a decade, 2 decades back. And this was all about technology. We were doing a project with CNRS France on INDOEX, Indian Ocean Expedition. So wherein we monitored and mapped all the Indian Ocean throughout, and we could see the aerosols, and we just corrected the monsoon model, the rainfall model. And this was a big beginning kind of work, which was even published on the NASA website. So as far as technology is concerned, I always advise, whenever we drive through our vehicles, then there is a message, a very nice message on our mirrors, that objects in mirror are closer than they appear. So the meaning is, we feel that the technology has not encountered, or the technology has not touched our lives. But very soon, within no time, the technology occupies our life. So this is true when you compare the spread of internet, the spread of cell phones, so which is much more faster than the spread of television. So you can imagine the way mobile has spread, or the way the smartphones are spread. So this has already, it has made a revolution in our life. So this kind of spreading of technology is called as exponential spreading of technology. And that's why today's theme, what we are dealing with, is a variable computing. And you will find that this technology is all over around us, and it is really touching our societal lives. Just have a look at this particular slide. In a time span of 60 seconds, 1 minute, what is happening, and whenever we are discussing about technology, just 1 minute, what is happening all over the world. So you will find that in 1 minute, that is a time span of 60 seconds, there are around 320 new total Twitter accounts are being created. In 60 seconds, there are 694,000 plus search queries on Google. 168 million emails are sent all over the world. As far as blogs are there, 1,500 plus blog posts are getting disseminated throughout all the blogs. 70 plus domain names are registered. So just like abc.com, there are around 70 plus domains, they are getting registered. YouTube's, you might be aware of, 600 plus new videos are posted in one minute. Okay, so you can imagine that with our smartphone, which is the medium through which we are accessing the technology. So this is the spread of the technology. So this particular slide shows how the technology is spreading and how the technology is bringing a new information revolution on in our lives, right? And all this thing is being assessed through the smartphone. So you will wonder, what is the capacity of smartphone whenever you are talking about this technology spread? So there is a very good picture, and this picture is, this is the processor in the smartphone, and this processor, and there are so many applications you are browsing through your smartphones. So the processor has become like this. So it is almost about to die, or it is almost about to having a lot of difficulty in dealing with the multiple windows you are opening, or the multiple applications you are dealing with. So in computing paradigm, I hope that in the audience there are many computing experts also. So this particular computing paradigm is called as von Neumann bottleneck, because our computers, the computers inside the PCs, the computers inside the laptops, they are like having the philosophy called as von Neumann philosophy. And this is the kind of fate of the computer, fate of the microprocessor, whenever they are dealing with, whenever you simply open multiple windows on your computer, you know that the computer is unable to cope up with your application. So this is the fate of the CPU. And therefore, as an information technologist, when you think about the research in information technology, you have to think about how new ways can be developed so that the processor efficiency can be improved, the processor throughput can be improved, how the memory technology can be improved. And at the base of all this is the communication bottleneck, because communication is very important between the memory, the data, and the CPU, which is processing the data. So therefore, all these things, they are having a kind of tight coupling And the research in computer science or research in information technology, of course, it is very, very close to research in material science, because of course the entire thrust of material science is also to lead to good materials so that all the computing paradigm can also be improved. Bill Gates, the information supremo, he has a law, and that law tells you about how the computing revolution is moving. His law tells that relative computation time needed doubles every 2 years. And that's the reason why your new smartphone becomes obsolete, becomes old within no time. Because new applications are coming, new apps are coming, and on one fine day, you will find that you don't have space to store the contacts. You don't have the space to open a new window. So after 99 such similar windows, the smartphone will give a message that now it is incapable to accept one more window. So that is because the computation time, the relative computation time needed doubles every 2 years. So every 2 years, new applications are coming, and your computer or your microprocessor or your smartphone becomes useless. And this has been compensated by Moore's law. So Moore's law talks about the number of transistors, doubling of number of transistors. And Moore has stated long back that the doubling of the transistors per 12 months or per 16 months. And that's how these two laws are actually, they are complementing and they are struggling with each other. And there is always a trade-off between Bill Gates' law and Moore's law. So in our curriculum, we talk about a lot of things. We talk about hardware, we talk about software, and a new term which is coming is called as configware. So for example, when your smartphone is being utilized, you must have noticed that the patches are done on the fly. That means whenever the new configuration has to be done from the manufacturer end, the configuration can be done only by switching off your smartphone, so that the smartphone will automatically reconfigure itself. And that is possible with the configware. So configware is the new term which is coming in the forefront and which is much more superior than the hardware and software. And with the cloud connectivity, with the connectivity on the fly, with the 24/7 kind of connectivity, it is possible to not only your smartphones, but your washing machines, and with the new technology, your refrigerators, your televisions, wherever the programming chip is there, it can be programmed with the kind of internet connectivity you have. Okay, so that is the beauty of the technology. You don't have to take your gadget to the shop. The shop can reach you through the cloud or through the internet connectivity, and it can get into your device and it can just configure the device. It can install the new version of the software. So all this is possible with the technology, and therefore this scene of technology is very, very important. Unfortunately, when it comes to academics, just the previous talk, it was all about materials, wherein there is a lot of synergy between physics, chemistry, material science. In information technology also, we expect a lot of synergy between the hardware, software, and configware. But unfortunately, this is not happening today, because today we even talk about all these disciplines in silos. We talk about electronics engineering in a separate manner, in isolation. We talk about programming in isolation. We talk about configure in isolation. So what's happening is we are just training our manpower in one particular domain. We are training our manpower just in software. And therefore, there are many hubs which are coming up in Korea, Taiwan. And one fine day, when a particular chip is not there, all your vehicles, you are getting a lot of time, even though you book your vehicle, because a particular chip is not there, GPS chip is not there. And that's the reason I would say that India missed the bus in hardware. And therefore, there is a need to come together. There is a need to do interdisciplinary research. There is a need to look at the things from the multidisciplinary perspective, from the market perspective. And that's what the information technologists are doing nowadays. Here is a beautiful picture. Whenever we talk about silos, whenever we talk about the things in isolation, the typical electronics engineer and typical computer science engineer. So you cannot teach hardware to a programmer, because programming is a cup of tea for everyone. Everyone can come and program. However, the hardware guy can do the programming in a very, very efficient manner. So therefore, I am again just emphasizing my point that whenever it comes to training, The training has to be in an interdisciplinary manner. And in just next few slides, I'll be just showing you what kind of things are coming up and why this kind of connectivity between the hardware and software is required. So nowadays, even our group is working on a new technology called as Neuromorphic Computing. In Neuromorphic Computing, there is a migration of programming to the structural domain. What we have seen now, that your smartphone or your laptop or your computer is getting a lot of burden due to softwares, due to a lot of applications. So now there is this new technology which comes at the abstraction using new machine paradigm. And this new machine paradigm is all about structural programming of the computers. So through this structural programming, it is possible to program the computers with small microchips, with small microcontrollers, with small embedded devices. And then it is possible to achieve the kind of throughput that is required in the market. Now, why this kind of throughput is required? Let's see a few examples. So in the picture, you can see a developer called as Steve Mann. This Steve Mann is the person who is behind the wearable computers. Now, what is a wearable computer? You can see that in 1980, the wearable computer was looking like this. There was a helmet. On this helmet, there is a camera. You can see the camera. There is a device which is required to focus the camera. There is a device which is required to listen whatever is going on. So this was the kind of concept was there in 1980. With the progress in the technology, this kind of helmet has reduced to a small device. You can see what has happened in mid-1980s. And then with this, what has happened in early 1990s? Because in early 1990s, there was a conception of microprocessor. There was a conception of miniaturization, so that the things can be made compact. So with this compact, what has happened in mid-1990s, you can see the device has become very, very small. So what used to look like this, a bulky device, now it has reduced to a very small device. And then around late 1990s, you can see that the entire device comes as a goggle. It can be wear on the eye, right? So the entire functionality like the camera, the zooming, the hearing the sound, the other parts like recognition of color, everything comes on the goggle, right? And this goggle, you know that there is a concept of Google goggles, and these goggles, now they are available. So this is the scale of technology. This is the progress of technology which is happening. And to enable this technology, we must have a kind of synergy between hardware, software, and how to make the things smaller, how to make the things miniaturized. And this is possible with the technology, progressive technology. Now, what are the applications? Why we are doing this? So you can see here, sensors are getting smaller. The programmable devices are getting smaller. Even some of the sensors like diabetic sensors, now they are available as even you can put it on the fingers. And this sensor has a kind of connectivity to the entire processing unit. So you can process the entire diabetic data. You can give alert to the patient when the sugar level is going to be increased. And there are a lot of such things which are possible. So what are the applications? Just now we have seen this kind of device. What is the possible application of this device? So you will just appreciate that this is possible to be used as an augmented memory. Now, what is augmented memory? Augmented memory is a memory which gives some kind of memory aid to the senior citizens. For the senior citizens, there are a lot of problems. Elderly people, there are a lot of problems with poor memory. So this kind of device, when it is there somewhere which is implanted, right? So it will help the senior citizens to remember name and face of the person who is coming in front of them. So these devices, they have a lot of image processing, and with image processing, they will just let the senior citizen know that this person who is coming in front of him or her, he has seen and what are the associated memories with that person, right? So these are the applications of the technology. And it will also help you in a normal way that suppose you parked your car in a big city and you forgot where it has been parked. So the camera on your body will record the parking space, the parking coordinates, and now all the this kind of devices, they have GPS connectivity. So then it is possible to know where your device, where your parking has been done and it will enable you to locate your car has been parked. This is the technology. Again, it is very much required, or it's a boon for visually disabled people, visually impaired people. So this visually enabled people, so they have very poor vision, or some people even they have night vision, so that night vision is very poor, or some people they have color blindness. So for all of them, these kind of devices, they will help in a great way to enhance the contrast, to adjust the colors, to have the night vision, to have the enlarged view. Okay, even for defense applications, sometimes you must have the enlarged view. So that enlarged view is also possible with the technology. So these are few applications, few more applications I'll be showing you. So one such application which is very popular with the technology is called as safety net, or it is called as creating villages in the city. Just imagine you are in Mumbai, a big city, and in this city you want to know a person who is in the crowd, who belongs to, or who is from your place, right? So in that case, this kind of variable users, they will be helping in a lot of manner, and they will help you to locate where that person is there from your place. And then you can form a small group, and these small groups can be formed even on the social net, and then you can start having a dialogue with all these people. So this is called a safety net. Secondly, this is also helping you to creating the villages of like-minded people in the city. Sometimes these kind of devices, they also help you to monitor the body parameters of the patient. For example, on the move, you can monitor the heart rate. On the move, you can monitor the perspiration or breath rate. And in this way, whenever some abnormal conditions are there, instead you going to the doctor, if you are in a very crowded place and you are driving a car and you get symptoms like heart attack, then instead you going to the hospital, an ambulance will come and ambulance will pick you up and it will reach you to the hospital. So these are kind of life-saving applications which are possible by using technologies. So even these applications are being used for defense purpose. There is a concept called as familiar strangers. So these familiar strangers, these are the people that they know each other and they are from common location, but they are ignoring each other in a crowd. So whenever such situations are there, this might cause some kind of security problems, some kind of terrorist kind of things are there. So do you know how the terrorists are going to be detected? Whenever such symptoms are there, then the technology will help, and the technology will, within no time, the background of those people will be brought to the forefront of the security agencies, and then it is possible to know that these two people, they are doing this purposely, and therefore they can be caught by using technology. So this is a concept called as familiar strangers, which is also possible by using technology. So fortunately, with technology, life is good. There are so many gadgets around. There is a washing machine, there is a laptop, there is printer, all these devices are there. However, having these many devices, how to use them, that's a real problem. Whenever you are using washing machine, you don't know whether there is a water in the upper tank or whether there is a water in the sump tank, right? So there has to be some connectivity between all these devices. So the connectivity between the your device and the cell phone will be a kind of boon, so that it will save you a lot of time. It will save you from confusion. It will save you from usage of the devices. So therefore, there is a need to connect all these devices. There is a need so that the devices can be connected to each other. The devices can be connected to living and non-living things. And then there is a network of all these devices. So this kind of network is called as Internet of Things. Fortunately, all the devices today, they have internet connectivity. All of them they are internet-enabled devices. And these internet-enabled devices, they can talk to each other. They have the compatibility to talk to each other. And then it is possible so that you can inculcate intelligence in all these devices. Okay. So here you can see that today communication is ruling, because all these devices, they can talk to each other, right? And then there is less human intervention is required. And with less human intervention also, the devices can talk to each other and they can take decision, so that not much human intervention is required and the work is done in a very, very efficient manner, right? So here you can see this is a concept which is coming in the forefront, which is called as pervasive computing. So pervasive computing is nothing but computing everywhere. Just imagine if you are sitting in a room, how many computers are there around you? There are thousands of computers around you. So those computers need not look like a real computer, like a laptop or like a desktop. They are there in your watches, they are there in your lockets, they are there in your cell phones, they are there in your washing machine, a computer is there in your television, a computer is there in the set-top box. So all these computers, they are there and they are talking to each other. So this is scenario which is called as pervasive computing, or which is called as ubiquitous computing. And this ubiquitous computing communication is possible by using a new technology, and this new technology is called as Internet of Things. So what is really seen, the devices are increasingly more. They are powerful, they are getting smaller, they are getting cheaper. People are interacting these devices daily with hundreds of computing devices. So many of them, they are compatible to your cell phones. So just imagine the kind of cars we have today. So they have all kinds of these computers. So even if you don't, if you forget to have the seat belt, then they will give you alert. So there is a small chip which detects whether you are putting the seat belt or not. There is a device which can fix your speed, and it will allow you to drive at a constant speed. So all these things are possible, and this kind of technology is called as pervasive computing or ubiquitous computing. And that is possible with a new kind of communication paradigm, and that is called as Internet of Things. So in the picture, you can see that there are different smart places. There are smart homes, there are smart offices, there are smart transportation, right? And there are smart rivers. With even your WhatsApp, today you can see whether you are approaching to a friend or you are going away from a friend, the location wise. So that is an application of smart technology. And this smart technology is possible because the integrated world, they are getting connected with the integrated islands, and then they are also connected with smart cities. So this kind of connectivity, which is called as the pervasive connectivity, is possible with the IoT. So here you can see that people, they are connecting to the things. The person having lot of sensors, the motion sensors, the ECG sensors, they are connecting to the things like hospital. Hospital is a smart place, and then automatically the hospital people will come to know that a person is having some problem or heart disease, and then it's possible to diagnose all those things. So in this way, today's scenario is more things are being connected to each other. So if you see around you, then more and many more things are getting connected. And other important thing is, things are also getting connected to other things, right? A vehicle is getting connected to other vehicle, or a vehicle is getting connected to your petrol pump, gas station. And in this way, things getting to connected other things is a very good scenario, because it is leading to complex and heterogeneous networks and resources. And as I said, we are moving towards, from any time, any place connectivity for anyone. We have connectivity for anything. So earlier we have connectivity anytime, that was internet, at any place, because now even in villages the internet is there and anyone can use this. But now we are moving to a new paradigm called as connectivity for anything. So here you can see any type of connection, any time connection, any place connection, and anything connection. So these three things, they are converging, they are coming together. And this particular revolution, which is just touching our lives these days, is the revolution of Internet of Things. A rough idea, we hear about how many devices are getting connected. Here you can see that day by day, millions and billions of devices, they are getting connected. So even a new protocol which has come on the internet, that is called as Ipv6 Protocol. And this protocol, because our internet is unable to give addresses to these devices, because every device needs to be identified, needs to be given address. So there is a need of something like 3.4 into 10 to 38 IP addresses, so that every device can be addressed, every device can be communicated. Now there is another problem with this revolution, and the kind of data these devices are giving out. So these devices are giving out tremendous amount of data, and therefore there is a concept of big data. We are talking about big data, and this big data is only because the data size is increasing And not only the data size is increasing, the kind of data is also not similar. It is a dissimilar data, and it is coming at a ferocious velocity, and therefore the big data word is used for all this revolution. So you can see here there are few examples of this. You can see that 3D printers example, or the drones which are coming in the forefront, or even the LED light bulbs, the new kind of light bulbs. They are all controllable. The intensity can be controlled, the color texture can be controlled, and this is all possible because of their internet enabled kind of nature. Even the 3D printers we have, even just recently in last month, IIT Kharagpur researchers, they have devised a technology by which the house can be built within 24 hours. Just input the design to the 3D printer, it will build the entire house with the walls, the doors, the kind of whatever the kind of inside architecture you want. The house will be ready within 24 hours. Now this is the miracle which is possible by using 3D printing. So this is called as prototyping, and the entire creativity can be converted into products. And here you can see that a lot of things are getting connected. Now, why we are moving to all these things? This is a beautiful house you can see, and this is called as Bill Gates' home. And in this Bill Gates' home, there are a lot of things which are connected to the other things. So such as, I'll give you one scenario. You are going to a shopping mall, and whenever you are going to a shopping mall, the things are talking to your smartphone. Suppose there is a milk packet in the shopping mall. It is just talking to your smartphone that what is the expiry date of the milk, right? And then with the shopping mall, it is just guiding the customer depending on the choice of the customer, depending on the taste of the customer, where the customer should move. It just recommends, right? So these kind of things are coming and possible with the Internet of Things. Another application is smart clothing. We get with nanotechnology, the earlier presentation, I'm just relating to the earlier presentation. So the textile, the conductive textile, and with the ink pens, now it is possible to have sensors built in the fabric of the person, so that it can monitor pulse rate, it can monitor blood pressure, it can monitor blood temperature or body temperature. It is just not monitoring. What it's doing is it is sending all this communication to the hospitals, to the doctors, to the family doctors, so that the doctor will come to know within a small time whether the patient is doing well or not, right? And the treatment can happen at a rapid rate. If you go to seminars, now you get this kind of interactive text posters. So these posters, they will communicate to your device, and it will just tell you that where you should move. So these kind of interactive text posters are possible with the technology. More serious applications. Here you can see that these pill cams are now available. So pill cams are nothing but it is a capsule, a medicine which is there, and in this medicine there is a camera, and you have to just swallow the medicine, just swallow the pill, and the camera will go on recording the inside of the body, because sometimes even with the latest technology it is not possible to see what is happening in your inside of your body. So these kind of devices, they can give the diagnostics what is happening inside the body, where the doctors can't even see with the specialized gadgets. So this will give a direct communication to the doctor that what is happening. And this is all possible with the biocompatible materials. So just the earlier talk was regarding materials, and these biocompatible materials, it is possible to have all these technological gadgets so that it can give a real-time information to the doctor. And there are many more applications, like intelligent parking is one application. The cell phones, as I said, they have all these devices. I'll show you some interesting applications. One application which is happening in the market, and it is really taken a lot of share of the market, is the Happy Pork. So this is a pork, and with this pork, whenever you are eating, basically the problem of obesity is simply because we are eating too fast, and the signal of hungriness, it is going from the brain to brain, and then brain fails to recognize when your stomach is full, right? And then we keep on eating because the brain processing the signal gets little time. So this kind of Happy Porks, they have Bluetooth connectivity, and they will just alert the person to eat slowly. So whenever you are eating slowly, the brain gets time to process the things, and then there will be a signal that your stomach is full. There is no more hungriness, right? And this kind of devices are also there in the market, and you can see that this is how the technology is really helping human beings just to save the life or just to have in a better health kind of thing. Another application you can see here, the new toothbrush which has come to the market is having the Bluetooth connectivity. So this Bluetooth connectivity will enable the toothbrush just to recognize whether it is going through each and every corner of the mouth and whether it is brushing the teeth properly, right? If not, if there is a cavity, this toothbrush will directly give a signal to your dentist that there is some problem, and then the dentist will approach you and the treatment will start. So again, these kind of applications are like life-saving applications. So there are other applications like the technology going into the refrigerators, glucose monitoring is possible, or even for your gardens, this technology can give you the kind of water, adequate water. Even there is a new fiction arcade machine with the artificial intelligence. It is possible to have the entire story which is written, the entire fiction, and there are packages. You just have to input the number of characters in the package, and then you have to just tell the package. You must have seen these days even Gmail is getting smarter, but more than that, there is now technology called the GPT-3. So with GPT-3, it is possible not only to write the fictions, but even it is possible to write research articles, because you must have seen that Stanford University and other universities now they have come out with a package. If you put the abstract of your research article, then there are packages which gives you some sort of guidelines, some sort of write-up, and which is much similar to your research article. Even if you check the plagiarism, then you will find that there is no plagiarism. So this is the kind of technological wonders which are possible, and they are helping the researchers, because there are packages. If you want to write the story and if you are not getting the words properly, then these packages will help you find out the proper words. So these are few applications, and I'll come to the last part of the talk, and this is about where the human life is coming into the picture, or where the research is coming into the picture. So with this kind of technology, as I said, the number of tweets or the number of videos with YouTube, the number of blog posts, they are all increasing, and slowly we are moving towards a era which is called as big data. So gone are the days when the data was computed with megabyte or gigabyte. Now we are talking about zettabyte. So what is the zettabyte? This zettabyte is nothing but, if you compare the height of the data, here you can see, then the height of the data is 25 times higher than the Mount Fuji. Mount Fuji is the benchmark for measuring the height, and even our today's data is crossing that benchmark. So this is the big data which is occupying our lives. And just to address the big data, we have a new computing paradigm where the hardware, software, and configware is coming together, and it is called as fog computing, right? So it is not even cloud computing. In cloud computing, we are not talking about the processing, but in fog computing, we are talking about the distributed processing. So with this distributed processing, it is possible to distribute the data with processing, right? So this is a kind of paradigm where the IoT and cloud converge together. And this is the big thing of the day, that where the IoT, Internet of Things, and the cloud, they are converging together, and they are solving all kinds of issues which is complicating the life with the data. And why not? This is also coming into the classrooms. So gone are the days. This was a traditional model of classroom wherein the teacher is lecturing and student is listening. We know that today we have the distributed classroom model, and we have seen in the pandemic that this model was used in a very efficient manner. So if we continue this traditional model, do you know what are the results? The results are traditional results. The teachers are still lecturing and students are out of cold, so they are not listening. So in this way, my appeal to all of you is to just make use of technology, because today we have flipped classroom, we have IoT in the classroom, we have all kinds of smart classrooms are there, and the boon of the technology. So with this, I would like to stop because my time is getting exhausted, and I'm really thankful to the organizers for giving me this opportunity to talk to you, all of you, on these areas of technological importance. Thank you very much.
Thank you, sir. Thank you for such a wonderful presentation, sir. Sir, we have a question from a participant, sir, if I can ask. Yes, sir. Sir, in what way IoT is energy efficient, and how community assists in the development of IoT?
Yeah, nowadays there are new kind of applications where the IoT is getting penetrated. One application is energy meters. So in energy meters, in the states like Uttarakhand, where getting the energy meter reading is very, very complicated and very complex due to a lot of problems. The technology is helping because all these energy meters, they are connected to the main server, and then the main server will record all the readings. Another application which I can make a mention of is the bridge monitoring devices. You must have read about the collapsing of bridges, right? Because they are not getting maintained properly. The maintenance schedule is not being followed. So for such things, the bridge sensors, they are talking to, again, the main maintenance office. And whenever the maintenance is not done in time, they will give an alert to the maintenance office, and then the maintenance is done in time. Or wherever there are cracks in the bridges, then the sensors will communicate to the maintenance office. And then it can save a lot of, you can say, tragedies due to bridge collapse. So these are few applications where the IoT is really helping the applications.
Thank you, sir. I hope the participant is happy with the answer. So it was really, really very interesting to know how technology has revolutionized and how it has changed our life, and how we have been access to different amazing tools and resources. Various gadgets and equipments has helped people lives to live more conveniently, and how science has changed our overall perspective of towards life. Thank you, sir. It was really amazing. We are truly enriched by your talk, sir.
Thank you so much. Thank you so much.
We now move to the next talk. Now I request Assistant Professor Dr. Santosh Upnikar, sir, from Department of Zoology, to introduce our next resource person, Mr. Aniruddha Pandit from Scotland, UK. Over to you, Dr. Supnikar, sir.
Thank you, Dr. Neeraman. Am I audible?
Yes, sir. Yes, sir. You are.
Okay, thank you. Good afternoon, everyone. It is now my great pleasure to introduce Mr. Aniruddha Pandit, our resource person for this session, who is going to talk us about from zoology to omics, changing perspectives in sciences. Mr. Pandit presently working as a project manager at PPD Laboratory, Belshell, GB Fleming House, UK. He has completed his Master of Science from the Shivaji University, Kolhapur, India in zoology, and also he has completed Master of Science in Bioinformatics from University of Aberdeen, Dundee, UK. Mr. Pandit has received license and certificates like Practice Project Management for Micro-Credential from University of Glasgow, and also for Scrum Foundation Professional Certificates. He has professional experience such as the project manager at Central Labs, as a member of a bioinformatics team in a genomic analysis cell established by the PHE as part of the COVID-19 pandemic responses. He mainly involved in performing genomic sequences analysis for SARS-CoV second genomic data, and also he has a bioinformatician web developer for various projects, collaboration between the UK and Brazil. As a lead analyst for the sequence analysis and report generation of the QCMD run EQA programs for HIV drug resistance, HBV drug resistance, HCV drug resistance, and CMV drug resistance. He also designed and developed of software modules for analysis, reporting, and report generation and online certificate generations. For the professional development, he attended various seminars and conferences on pest management sciences, neuroendocrinology, quality assurance, professional programs, and bioinformatics. He also has present his work data in the form of talks and posters. He has published several research articles in high impact reputed journals. This is a very brief introduction of our resource person. We all value such a expertise, which has been continuously working on various viruses, including COVID-19 and its variants, in order to find solutions to protect the human race. We are greatly honored to have Mr. Anita Pandey to present the plenary talk. Please join me in welcoming him, and I request him to share his experience. Thank you.
Thank you, Dr. Supnekar. Can you hear me, everyone?
Yes,
Excellent.
sir.
I'm just going to share my screen now. Just let me know when you can see it. Is that visible? Excellent. Right. Good morning, everyone. It's a bit early for me here in Scotland, but I think it's one of the great opportunities for me to come and speak here, along and sharing the stage, so to say, with such dignitaries, such experience, such experts. I'm absolutely honored. So thank you again for the opportunity. I'll just get to my talk in a minute, but I just want to say thank you to the principal, Dr. Ganesh Thakur, the invited guests, Professor Ray Prasad and Professor Kamath, all the dignitaries and participants of the conference, and of course, a special thanks to my good friend, Dr. Supnekar, for introducing me in such a kind way. My talk is going to be about from zoology to omics, changing perspectives in science. What I want to focus on, if I may, is the fact that I come from a small town called Wye in district Satara. I've been in Glasgow for almost 20 years. This on the left you can see Wye, and on the right you can see Glasgow. You can see the similarities between them. There's a river running through them. There's bridges, and both of these places I call home. This is basically just I wanted to share this to show that from a small town you can actually reach great heights and great experience through science and experience. So, namaskar, everyone. I'll give you a quick brief of my talk. I'm going to talk a little bit about me. Again, I don't think I share as much experience as my fellow speakers today, but I will try my best. I'll give a brief introduction about omics, the actual field of omics, followed by some actual applications of bioinformatics in research. Give a brief overview of the research projects I've been doing or have done in the past. And I will discuss one specific research project as we come. All these photos you see in this slideshow, all are taken by me. They're all of the University of Glasgow mostly. It's a very beautiful city. Okay, so quickly on to this. Dr. Supnekar has already introduced me and spoken about my various educational progress. I'll just continue on that. I did my master's in zoology in Shivaji University, Kolhapur. This is where me and Dr. Supnekar were actually classmates. I followed that up with a master's of science in bioinformatics in Aberdeen, Scotland. I have worked both in industry and academia. In industry, I worked as a data analysis, a software developer, and currently I'm working in project management. When I'm working in academia, I was working in the University of Glasgow as a bioinformatician/research technologist. So I have done my master's in zoology, but however, I've moved into bioinformatics, something which is sometimes scary for people in biology to go into something in IT, and vice versa. People in IT maybe daunted by the fact working in biology, but bioinformatics is there to help you understand that both can work together. I'll come on to that in a minute. Just to let you know, I'm currently working as a project manager in PPD in Global Central Labs. We do a lot of clinical trials and and clinical monitoring, other medical writing, quality assurance, etc. So there's quite a lot, but I won't speak about that right now. As I said, my previous job, I was a bioinformatician. I was a researcher in the University of Glasgow. These are my colleagues there, and my bosses for Shireen Davis, Professor Shireen Davis and Professor Julian Dow. I was working in their laboratory. I followed that up with a role in the Public Health England sector as a senior bioinformatician. This is during the COVID period. I thought I would use my experience, use my expertise to help out in the response that was required during this pandemic. So we were analyzing data and doing trend analysis and informing the government to help them inform, make policy decisions and support essentially the wider pandemic response. So I played a small part in it. So, but I think we did help out a lot in the UK. And bioinformatics essentially did help out a lot for that purpose. So I'm just not going to go into too much detail. You may have studied about bioinformatics in your curriculum. You may know about bioinformatics hearsay when you're hearing about it. So I'm not going to go too deep into it, onto something that you can actually Google or speak to your lecturers about. What I am going to do is just tell you what bioinformatics as a definition. It's basically, to the layman, it's a science of storing, retrieving, and analyzing large amounts of biological data. It is not only a field restricted to biology or computing, it is an interdisciplinary field. It involves biologists, computer scientists, mathematicians, data analysts, biostatisticians, biochemists. So many fields come together under the umbrella term omics or bioinformatics as it's known. It basically does form a major part of modern biology. You must have studied it in some form as part of your studies now, because it is very much integrated in our studies, in our research, in our work, etc. So coming to Professor Kamath, I think he was speaking about big data. Now, biological data is also quite large. It needs to be managed. It needs to be analyzed. It needs to be studied. So that data, what sort of data are we talking about? We can talk about RNA, DNA, protein data for basic, but also other genomic data, metagenomic data, transcriptomics, drug development, chemoinformatics, evolutionary studies, metabolomics. All these various different studies come under the umbrella term omics, and therefore it opens up a vast array of areas that a person can go. There is no niche in bioinformatics. They are all fields that can be explored, are being explored, and are being used to improve our daily life right now. Right? I'm sorry? Everything okay?
Yes, sir. Everything is okay. Go ahead, please.
So, everyone knows about COVID-19, the SARS-CoV-2 virus. Everybody has probably, unfortunately, may have seen its effects or had effects of its own. It was huge for the past 2 years. It is still going on. Hopefully now we're trending downwards towards it. I'm not going to talk about COVID-19 because I don't think anybody wants to learn more about COVID-19, or maybe they do, but there is a lot of research available at the moment. I just wanted to point out that bioinformatics played a major role understanding the virus, understanding the structure, understanding the various variants which were out there, understanding how they affected individuals or groups of people, the trends which occurred due to the infections which were caused, how a vaccine was developed, or now multiple vaccines have been developed for various for the COVID from various companies, from various institutes, from various. Bottom line, from research. And as I said, omics played a major role in this, in the research towards this. So I'm going to continue now with understanding from an individual perspective, from a student perspective. If you are a student who is thinking about a career in bioinformatics, but you think you're not in the right sort of field, because sometimes we believe, oh, I'm in biology, I'm going to do zoology, I'm going to do specifically in, say, ecology or in physiology. I'm not going to move away, I'm not going to branch out into other sort of things because that is not my field. No, that is incorrect now. Everything is interrelated, as I mentioned before. A person who has done zoology before, like me, we accumulate and utilize various skills, various different aspects of different fields. For example, my background is in cell biology. However, I also worked with molecular biology, systems biology, genetics. Somebody who's in IT majorly works with database management, programming, web development, cloud management. Some people who are specifically bioinformaticians, they work with databases, bioinformatics tools, data science, etc. What bioinformatics or what omics does is allows you to interrelate all of these. And myself included, I was very afraid of IT, but now I started programming, I created databases. So for creating applications, you can, for example, sequence analysis, function analysis, structure analysis, these are just some of the examples. And the various sort of subcategories within all of these applications. As you go on, you learn more about them, you start to apply them in real world applications. When I say applications, doesn't just mean a computer application. It means, for example, creating a vaccine can be considered as as an application. Creating a pesticide, which is greener pesticide, can be considered an application. And this is what I'm going to be talking about further in my slides. So the focus of my talk now will be bioinformatics in research. So I'm going to be talking about my time in the University of Glasgow and the research that I was doing there as part of my, my daily roles and responsibilities. So the Dow Davis Lab, essentially, they are quite famous for using the Drosophila. They have various multiple publications in the field of insect physiology, systems biology, etc. One of the main things that they've discovered or understood the functionality of is the Malpighian tubules, or the kidney sort of equivalents in Drosophila. So they're using Drosophila as a model to understand kidney function and regulation, and using that to understand what can be done for the human being. When you're using Drosophila as a model, you're basically using it to understand what can be done in that particular insect model that can also be done, replicated in humans. So insects as models was basically used. My job, I mean, apart from basic science, insect biology and biomedicine, which is there, including understanding kidney stones, understanding inborn errors of metabolism, with regards to basic science, understanding transport, signaling, stress, etc. My job, my roles included understanding and studying transcriptomics, functional genomics, metabolomics, among other things. So this is what I was working with. So the genomics big question is, what do genes do? As we understand, we know that there are multiple thousands of genes in our in everybody's DNA, and they perform various functions. So for example, cell communication, localization, transport, cellular component organization, apoptosis, etc. So there are multiple actions which genes do, but also what's important to understand is there are quite a large number of genes which are still unclassified. We do not know what those genes do. So I think around 20,000 genes are known, of which we don't know a chunk of them. We don't know what the actual genes do. So that's where bioinformatics, or genomics in this case, genomics, understanding the genes, that plays an important role. So in our lab, what we've done, I've helped in creating functionality such as the Fly Atlas 2, which is a Drosophila gene expression atlas. This is essentially a database where you can go and understand each of the genes inside the Drosophila and correlate them to the humans. You can understand, sorry, I don't know why my slides are going running ahead of me. So yes, so this is one of the functions which we made. Again, this is using RNA sequence data and microRNA sequence data. We're looking at various transcripts. We're looking at the genes. We're looking at their FPKMs, the enrichment of these genes for various parts of their body. This can be correlated to any organ or system in the human as well. And this is what is used as as research very majorly. It's highly cited, this particular paper, and I was very, very lucky to be a part of this group which was working on Fly Atlas 2. This is something which I created myself. The idea was to create and just like Fly Atlas 2, which is specifically for Drosophila, we wanted to look at creating an atlas, or so basically a resource for pest insects. This was the major field of my research, pest insects, and creating greener pesticides. To get rid of chemicals in the ecosystem, we want to look at affecting regulatory behavior of insects. So anyway, so I'll come to that point later. So this was, again, create an application I created where we could look at different pests. There is a sequencer, so you can look at their genes, you can blast genes, you can search for genes, you can look at their expression. All of this application, again, me as a biologist, you'll be amazed to know that this is written in Python with a Django framework. These are terms which maybe IT people will know, and they'll be like, yes, okay, I understand. It's maybe not for biology, but let me tell you, I'm a biologist who's working with IT, so it can be done. So let me talk about NeuroStress PEP. This is the main project that I was working on for 4 years over there, that I was in the research. This is a €7 million project. It was granted by the Horizon 2020 grant. There were 14 collaborators across Europe. The aim of this was to generate novel biocontrol agents for insects, pests from neuroendocrinology, and to use the insect's own neuropeptide hormones. So we were going to not use any external chemicals per se, but we were going to try and influence the behavior of the insects to not behave as pests. Now, the reason why we don't use chemicals is we do not want to harm beneficial insects. There are also beneficial insects like bees, butterflies, etc., which are important in pollination and other functionalities. We do not want to harm them. What we want to do is we want to focus specifically on target pest species. So this is a green method of control compared to current insecticide. This is a very successful grant, and quite a few papers were published in it. Another application which I created for this was again a paper that I authored and an application I created, a database for insect neuropeptide research. I would recommend if you are interested, go and have a look at that as well. But yes, let me continue. So as I said, quite a few publications came out of this project. These are just some of the ones which I was involved in. There are, however, many, many more publications as part of the project. So I'm going to focus on one particular project that I was part of, or rather I authored, is the evolutionary trends of neuropeptide signaling in beetles. I'm going to speak specifically about this paper right now. Many of the members of order Coleoptera, which is this essentially beetles, are found to be economically significant pest species of various agricultural and silvicultural plant species. So we're looking at beetles essentially, which have been considered as pests. There are various examples of that. I'll come to them in a minute. So as part of the NeuroStress PEP project, signaling peptides, and particular neuropeptides and protein hormones, were identified and studied as possible insect control agents. So these the insect's own neuropeptides. The neuropeptides are the proteins which regulate their behavior. These were being targeted as insect control agents. This was for creating effective integrative pest management strategies. So in this particular study, what we've done is we've aimed to perform comparative neuropeptidomics. So what we're doing is we're trying to understand the neuropeptide profile of each of these beetles. Some of them are pests, some of them are not pests, some of them may be beneficial, for example. So we want to understand what is their neuropeptide profile. Is there any differences in the neuropeptide profile? Is there anything which causes them to become a pest? So we're looking at all this information in this particular project. So how do we do that? So we're looking at the omics data from up to 31 coleopterans. That means from 31 different beetle species, we took the omics data, including transcriptomics as well as genomics data. The species include the suborders Polyphaga and Adiphaga, and representative species from their underlying species. So all these are from these two particular suborders. The neuropeptide precursors and mature peptides were identified. As I said, a neuropeptidome, as it is called, it was created for each of these insects. And then comparative neuropeptidomics and evolutionary analysis was done to gain an insight into gene conservation and differentiation. So let me start on essentially neuropeptides. I'll give you a quick overview of this. Neuropeptides are essentially chemical messengers that circulate in the body and control bodily processes. Neuropeptides are proteins. They are responsible for regulation of a variety of physiological functions. So these include, growth and development, digestion, metabolism, ecdysis, water balance, ion homeostasis, and of course, neuromodulators. These are just some examples of what they are known for. So they are known for understanding signaling neurotransmitters, for example, for salivary gland management, for blood feeding uptake, for ecdysis, as I mentioned before, for feeding satiety, meaning are they hungry, are they full, for cuticle synthesis, for other activities like diuresis and post-mating reproductive activities. All neuropeptides are absolutely responsible for many of the physiologic functions, as I mentioned. So an example of this is how do neuropeptides, how do they affect the behavior, the feeding behavior, for example? How do they regulate the feeding behavior in an insect? So, for example, the insect gets hungry. It understands that there is a lack of energy and it needs to feed. So what it does is starts looking for food. So some neuropeptides focus on understanding that. Some peptides will use, affect muscular activity to move. Then once it's found, the neuropeptides will tell the insect, the brain will start eating now. It will eat. And then once it's full, the brain will send another signal to disengage feeding. So all of these sort of functionalities is determined by different neuropeptides. So for example, stimulation, sulfakinins, tachykinins, proctolin, allotropins, etc. are used in stimulation when they are hungry, what they need to do. Inhibition, myosuppressants, allotropisatins, myoinhibitory. So these stop the feeding. Once it's done, we need to now stop, and the cycle continues. So there are, of course, other neuropeptides of importance. Example, and one of them, of course, is the diuretic hormones, but we'll come to that in a bit. Okay, so what species did we use? We use, as I said, we use around 31 different species. We used from the Adifiga, which is one of the ancient orders. We used 3 different species from there. Gyrinus marinus, Carabus granulatus, and Amphizoa insolens. We used 3 of them there. And from Polyphaga, we tried to look at as many different suborders as possible. And we look at, for example, pine weevil family, or the ladybird family, or some other flower, the red flower beetle, etc. So we've got quite a few. We've looked at scarabs as well. We've got quite a diverse variety of beetles, ranging from, as I said before, beetles that are considered as pests, as well as beetles that are considered as beneficials. If you look at their species tree, you can see Adifiga and Polyphaga, the 3, they're quite ancient. They're 170 to 190 million years ago. These were established. Okay. The others, you can see that they are quite young, from 100 million years ago to 200 million years ago in the Polyphaga suborder. So this is the species tree to show the various insects and where they lie as in the evolutionary tree. Okay, some of the methods and tools. I'm not going to go too much detail in what they was used. There are, of course, publications for each and everything available, but I'm just going to give you a sort of a brief overview of how we went about doing the various tasks to get, first of all, to get the information for doing the analysis. So first you need to do the transcriptome assembly. Essentially, transcriptome assembly is you have lots of raw sequence. What people do nowadays is they do the sequencing, because sequencing is much cheaper now. They just do the sequencing and If they don't work on the sequences themselves, they make it publicly available for other researchers to use that sequences. So most of the sequences that we use in this study have already been sequenced by other labs, by other researchers who were kind enough to give access to these things. So what we had to do was then just take the raw sequences and put it together doing transcriptome assembly. We used de novo analysis for this, i.e. there was no reference sequence to check against. So we used de novo analysis for creating the transcriptome assembly. Other tools which we use, of course, is FastQC to check the quality, digital normalization to check, again, make sure the sequences were normalized. We use Trinity, which is a de novo software for assembly, and we use Busco to verify these sequences that we have we have assembled. The next task, of course, was neuropeptide prediction. We had to understand what neuropeptides were. We had to find out the sequences of the neuropeptides. We had to do the sequence analysis on that. And finally, we did phylogeny analysis, i.e. to look at evolutionary trends for the various insects, transcriptomes that we discovered. That we analyzed. So as a bioinformatician, one thing which you will learn to do is create pipelines. Pipelines is essentially different softwares linked together so that you don't sit and do one task and then wait for it to finish. And then because it could take hours, it could take minutes, it could take days, sometimes it could take weeks. What you need to do is you not stop at wait for it, but you allow the computer, the machine, the server, the high HPC that you're using, all of it to do it on its own. So what you do as a bioinformatician is you create a pipeline which will do all the steps, necessary steps, as much as possible with less human interaction to avoid issues with discrepancy with manipulation, manual manipulation, which could cause issues. Try and make a pipeline of all the activities. So what we're going to do is first, for the transcriptome assembly, we have a pipeline there which looks at the raw reads from the raw sequencing, RNA sequencing, We do normalization, trimming, we do the assembly, and then we do the quality control and verification. And we get the transcripts from that. From these transcripts, we did for using, as I said, for neuropeptide prediction, we did sequence alignment, we did determination of signal peptides, peptide cleavage site prediction, and then from that, we got the precursors and the mature neuropeptide sequences. We did a secondary analysis finding out, we did a secondary analysis finding out the neuropeptide receptors as well, but that is not part of this. This was done as a secondary analysis. Because we had the data, why not have it for somebody else to do? For this paper, we didn't specify our analysis in this paper. Further on, we did multiple sequence alignment, phylogeny, sequence conservation, and CD searches and transmembrane searches. So these are post analysis that we did as well for confirmation of and the neuropeptide. So quick discussion on the results. So as the stats you see in front of you are essentially the assembly stats for each of the beetles transcriptomes or / genomes that we did. Most of them were paired end, some of them were single reads as well. And you can see the number of bases for each. There's so many bases per thing. So we had a lot of information that we could work from. We had a lot of raw transcripts which we could work from, a lot of genes, as they call them. We understand that, please understand that when we're saying genes, they are not defined. They still need to be defined, and the process goes on further. Let me just continue. So quite a few post-transcript assembly tasks are done. So Busco verification is done. BLAST analysis is done with various different databases. KEGG analysis is done. Ontology annotation is done. As I said, we're comparing against known. When you do a BLAST search, let me just tell you, is basically trying to understand from the sequences that you don't know what they are, comparing to sequences that you do know what they are. Once you compare these two to each other, you can put a relation to say, okay, my sequence matches this much homology with a known sequence, therefore it could possibly be that particular gene. So there's steps in that as well, which are involved in that. But what we did was we did that, and we started on the neuropeptide precursor and mature peptide identity. So essentially what we got is from all the transcripts, all the genes that we had to focus particularly on the ones for neuropeptides. So first we had to find out the precursors. So we identified the precursors by comparing against known precursors. Sorry, okay, so we compared against known precursors. What we did is we identified the mature peptides, we identified the cleavage sites and any other sort of signal peptides. Sorry, this is signal peptides and the different mature peptides within each precursor of each neuropeptide within each beetle. So you can imagine 31 beetles, around 50 neuropeptides each, and within the 50 neuropeptides, there are different segments for each of them. So that is a lot of data to analyze. Thank God for computers there. So we have done, we identified all these things from all the different insects, from all the beetle transcriptomes that we had, and we still needed to verify whether these were still the correct neuropeptides. So what we did was, before creating the profile, of course, I'll come to that. So from all the information that we had, we created a neuropeptide profile for each of the beetles that we were under the study, and each of the neuropeptides that we identified within the beetles transcriptome. The black boxes mark the neuropeptides that were not found within the beetles transcriptomes, while the gray ones show that they were found. So this is just, as I said, a profile. So there are some which have absolutely no profile, no neuropeptide was found at all in any of the beetles. There are certain characteristic neuropeptides that are not found. For example, cortisonin is one of them, and kinin is one of them, which strangely enough, in one of the ancient transcriptomes, they did find and identify one kinin there, a neuropeptide there, which is very interesting. So for all the others, this was the neuropeptide profile created. So as I said before, we needed to verify against other among themselves as well, but as well as known neuropeptides to see whether they share the same pattern. This is done, essentially it's pattern matching when you do blast searching. It's checking whether they are there and then putting them all together to make a consensus to say, yes, this is essentially definitely that neuropeptide. So for various, as I said before, for the various neuropeptides, for each insect, we looked at all the different mature peptides, and we made a list of them, and then we looked at their consensuses and we checked their profile. Again, this is all verification. Still, we're into the verification. This is not biologically proven. This is still just on the computer. It's telling you, we think that these are putative neuropeptides. So it's the next job is you go to you take these sequences, you take that information, go to the lab. In the lab, you try and identify the neuropeptides genes again to verify this information. So it's all a circular thing, but bioinformaticians help the job, making the job much easier, as I said before. So we're looking at the patterns by using different software. You can look at the conserved regions. You can see, okay, yes, that is definitely an allostatin B because it has W and W and 1, 2, 3, 4, 5, 6, 7 bases in the middle. Amino acids in the middle. So by doing consensus analysis, by doing multiple sequence analysis, we can verify the genes that the mature peptides that we have, also the genes that we have for each neuropeptide. So coming to the part of this study, this is the last part. We're looking at evolutionary trend analysis. We wanted to find out why or what sort of over time, what has caused these pests to become pests? Is there any evolutionary significance to that? Is there any trend analysis to that? So we're looking at all these by comparing the neuropeptides profiles of each of these beetles to each other, as well as using certain sort of certain characteristics, certain behavioral patterns, certain physiological patterns. So I'll come to that in a second. So when we're doing evolutionary studies, we're looking at phylogeny. We're seeing how close each of these insect neuropeptides are to one another from an evolutionary perspective. How close are the precursors to each other? So what you're doing is you're looking at all the sequences for all these neuropeptides, for all the beetles, putting them together and trying to come up with a trend analysis of the evolutionary pattern. Is there any similarities? Which groups are similar? Why would they be similar? Is there any characteristics that group them together? So we're looking at all this information. So we did that for the precursors as well as we did that for the mature peptides. So we've broken down into the mature peptides. So this is just examples for allotostatin C and short neuropeptide F. As you can see, this grouping of the mature peptides, most of these are very similar to each other except that one there who's something is off there. Although it contains the same pattern, there is something there which makes it individualizes it from the others. There's a small group here as well. So these are quite interesting things to look at when you do the evolutionary analysis. What we did further on, just to see, as I said, behavioral patterns or physiological patterns. So this is a heat map essentially which we've created for the neuropeptide profiles of each of the species. And what we've done is we've grouped it from oldest, so these are the oldest ones, to the youngest ones. And each color in that is telling you sort of the age range that they are. And we want to see if this sort of trend analysis, is there a difference between the number and the actual neuropeptides in, let's say, ancient orders or ancient insects versus younger ones. So when we say younger ones, these are in million years, so don't be fooled by the numbers. As you can see, the older ones seem to have less neuropeptides for their functionalities, while the newer ones seem to gain a bit more neuropeptides for maybe different functionalities. That's quite interesting. So it would be interesting to look into that. A similar trend, what we did was we did it for diet. So to understand the diet of the various insects, so we understood what sort of diet are they? Herbivorous? Are they polymorphic? Are they eating everything? Are they predaceous? Are they saprophagous or xylophagous? So from this trend, we're looking at trends there, and we see that most of the predaceous ones, many of the neuropeptides are missing for the predaceous, while for the herbivorous, we've got quite a strong sort of section of neuropeptides here, and a smattering here. So polymorphic, of course, as you can imagine, they're eating all sorts of food. So that therefore they would need more different neuropeptides for looking at that different point. So that's another interesting point there as well. And finally, this is for size. So based on their adult size, so what we did is we looked at the sizes of each of the beetles from if they were, what size they would be as an adult, what is the average size they would be. So you can see the size here, it ranges from 50 mm, that's quite a big beetle, to right to 2.5 mm, which is very, very small. What does the neuropeptide profile change according to the size? Is there any differences that is seen there? So we looked at that analysis. There's some interesting theories as well. The bigger ones seem to have less neuropeptides compared to the smaller ones. Is that something which affects their pest behavior? Most of these smaller ones are pests, while the bigger ones are not really considered to be pests as such. So quite a few interesting trends and analysis that we discovered. Hopefully it will be taken forward. So just a quick summary. So using bioinformatics pipelines, we assembled and analyzed sequence data of more than 30 members of Coleoptera. We identified their neuropeptide precursors and the mature peptides for each of them. The species included suborders, as I mentioned, Polyphaga and Adiphaga, and therefore they were representative of many wide diversity, a wide variety of species under these suborders. We also looked at the evolutionary development and trends in terms of gene conservation, differentiation of neuropeptide families, and across the coleopteran species to get a better understanding of their functionality. So I just wanted to show you with this how bioinformatics can be used in a particular way, but there are multitude of uses of bioinformatics, and it is, as I said, it is permeating into every field, and every field is permeating into this. There is a lot of collaborative science happening, and I really would encourage everyone to keep an open mind and work towards it. So for this particular project, I would like to thank Professor Guy Smee, Shireen Davis, and Professor Julian Dow, and the Neurostress Web Consortium for that particular project. And that is my talk. I'm absolutely happy for any questions. I'm sorry if I rushed through, but I hope it was interesting enough to keep you engaged. Thank you.
Yeah, sir. Yeah. Thank you so much, sir. It was really interesting. Since this bioinformatics or genomics, proteomics is the youngest branch, we can say, in the life science, and we hardly means like those who study will know, but those who don't hardly know about it. So there's maybe it's out of my curiosity. I just wanted to know that when you do the evolutionary relationship or the pattern of behavior in the beetles, how close, like as in human race, how close are we with the neuropeptide profile sequencing, whatever you have done?
Well,
yeah.
Oh no, that's a very good question. We are. I mean, I wouldn't say we are too far away.
Yeah.
Most of our genome is pretty much similar, but certain as you of course will be aware, certain genes are expressed more depending on the species, depending on what you are. As a human being, you may not be needing to become a pest and go and raid raw wheat fields, etc. So it depends on that. So the focus of this is what genes are expressed in what species. So the similarities will always be there. It's which ones are expressed and which are not. That is the difference there.
Okay. Thank you so much, sir. Thank you for sharing your expertise on omics. I hope the student will really benefit from your talk, and the student will develop new insight in the new domain of genomics and proteomics. Thank you, sir. It was really nice to hear you. Thank you so much.
Not a problem. Absolutely my pleasure. Thank you very much.
Thank you, sir. There's a small announcement for all the paper presenters who will be presenting the research paper before we conclude. First of all, I would like to thank all the participants. Thank you for your overwhelming response to our e-conference. As Principal Sir has said, we have received 80 plus of research papers for oral presentation. And the research paper are categorized into 3 groups, that is material science, bioscience, and information technology. The papers will be presented in separate breakout rooms of each group in the Zoom meeting platform itself. In the screen, you can see on the left top, there is a breakout room. So I will request the paper presenters, the participants, to kindly rename yourself, because the schedule of your presentation is already shared with you on the Telegram group and the WhatsApp group. So I request all the participants who will be doing the oral presentation to rename yourself and click the icon that is on the top left for the breakout room. There are 4 separate breakout rooms for material science 1, material science 2, bioscience, information technology, and mathematics. So you are requested to first rename yourself, and after the vote of thanks, I kindly request you to shift yourself in the breakout room. So I hope the announcement is clear to one and all. So we now come to the end of the formal inauguration function, because after a 5 minutes break, we'll continue with our presentation session. End of the story is the new beginning. On this note, let's conclude a remarkable, memorable, and the knowledgeable event with an word of appreciation and gratitude. To express vote of thanks, I request Ms. Sonu Tanwar Madam to kindly propose a vote of thanks. Towards you, Sonu Madam.
Thank you, ma'am. Good afternoon, one and all. Science knows no country, because knowledge belongs to humanity and is the torch which illuminates the world. So with this beautiful quote by Louis Pasteur, I would like to conclude today's e-conference. All the esteemed dignitaries and participants present on the online platform for the International E-Conference on Advances in Material Science, Bioscience and Information Technology, organized by the Faculty of Science in association with IQAC of Mahatma Phule Arts, Science and Commerce College, Panvel. It is such an honor for me to extend a vote of thanks to all those who have contributed for the successful organization of this e-conference. At the outset, I express my deep sense of gratitude towards our most valued invited guest, today's keynote speaker and resource person of this e-conference. First of all, I would like to express my gratitude towards Honorable Professor Nirish Rivaprasadu sir to take out time from his busy schedule to grace the event. Thank you, sir, for inspiring and encouraging us with your thoughts on functional nanomaterials from precursors, synthesis, characterization, and energy application. We are all inspired by your great words. Thank you, sir. I'm thankful to the resource person, Honorable Professor Rajneesh K. Kamath, sir, who shared a deep sense of knowledge about new computing paradigm and how science and technology occupying and incorporating in our lives, and supported this e-conference and enlightened the occasion with his talk during this conference. I'm also thankful to our second resource person, Honorable Mr. Aniruddha Pandit sir, who enlightened us with his scholarly talk on From Zoology to Omics, Changing Perspectives in Science, and how omics and bioinformatics plays important role in assessing and evaluating genome mapping. Thank you, sir, for sharing your valuable time and views with us. I sincerely put on record my gratefulness to our dynamic and visionary principal, Honorable Dr. Ganesh Thakur, sir, for his invaluable assistance in making the conference a success. I am very much thankful to Mr. S.L. Gove, sir, IQSC coordinator, Mr. A.G. Rokde, sir, convener and vice principal of science faculty, Dr. Pramod Thakur, sir, co-convener from the Department of Chemistry, and Dr. Girish Gun, sir, organizing secretary from the Department of Physics, for organizing this e-conference. I should be thankful to our teaching technical team and Professor A.M. Palve, sir, Mrs. Nandini Gaikwad, madam, Dr. S.P. Supnikar, sir, and Dr. Leena Meshra, ma'am, to coordinate this conference successfully. I must say thank you to our teaching fraternity for their active involvement and contribution for making this conference a happening event. I must appreciate and mention the involvement of the participants from various countries. I am grateful to all the participants who made this conference a great success. We thank you for being with us. It has remained a pronounced pleasure. Have a wonderful day ahead. Thank you, everyone. Thank you so much.
Thank you, Sonu, madam.
Thank you, ma'am.
Once again, I'll make the announcement very clear. In the Zoom meeting itself, there is a breakout room. There is an icon for breakout room. For all the participants who will be presenting the paper, there's a breakout room icon there. The schedule for the presentation is already shared with you on the Telegram and the WhatsApp group. So the participants know where they belong. That is Material Science 1, Material Science 2, Bioscience, Information Technology, and Mathematics. So in the breakout room, you have to kindly click on the icon and go into your respective rooms for the presentations. We have categorized for the presentation into four breakout rooms. All the participants are requested to kindly click on the icon for breakout rooms and shift to the rooms. Or else you can also rename yourself where you belong to. You can rename yourself on the Zoom where you belong to, and we can shift you in the respective categories. We can manually shift you in the respective breakout rooms if you rename yourself. I hope that